do you see way back on my back wall there where I'm pointing?
Yeah.
Yes.
That's the poster from the Amitsur meeting 50 years ago.
Dear me. The one behind the glass door?
Yeah, yeah. I'll move the door. No, I guess that's 1989, so it's merely 30 years ago.
Oh, yeah. When he was still alive, in his honor.
Yeah, yeah. So. The only poster I have in my office, except over there, which you can't see, I have AMS pictures of Hilbert, Emmy Noether, and Gauss,
Uh-huh.
who I call my three amigos.
So there's a potter up in Vermont who likes to make mugs with the pictures of famous people on them. And I was trying to convince him, I've known him for years, but I'm trying to convince him to make mugs with famous mathematicians on them. My first one was Emmy Noether. I'm not sure I succeeded, but Don, would you buy such a mug?
Yes.
Okay. Market research here.
Yeah, okay. If it wasn't too expensive.
It wouldn't be too expensive, but he's a Civil War buff. So most of the ones he's made so far, and he's made a lot, are generals from the Civil War and stuff like that. You know, Washington, Lincoln, all the usual people like that. Uzi, can you hear us? Yes. Uzi, who's running this meeting? Well, I think he just voted.
I'm willing to buy also one of the mugs.
Oh,
You know,
good.
the shekel is strong now.
Yeah.
So even if it is expensive, I will buy.
Uh-huh.
But with Hilbert, it would have to come with a hat, wouldn't it?
Yes, it would have to come with a hat.
I don't see Louis Rowan.
Hi.
I don't see him either. That was my impression that he was going to run it, but not from the seminar room.
No, he was supposed to connect from home or from here.
Uh-huh.
I'm calling him.
Okay.
We have to wake him up.
Yeah, well, you know, it's what? 3 o'clock in the afternoon?
Oh, well, he had his nap.
We'll leave it to Uzi to deal with this,
Okay.
since he knows full well who would be second in line.
Yeah, that would be scary.
Well, yeah. Yeah, mostly Louis really wanted to do this 40 minutes of reminiscences, so
Sure.
it would be appropriate for him.
I don't know.
Hi, Claudio.
Hi, you hear me?
I hear you
Yes.
fine.
Hello.
Yeah.
Hello, Alan. You're
Hi.
muted.
So we are here waiting to reminisce.
We're here waiting to reminisce. this was supposed to be organized by Louis. And we don't see him yet.
Okay, anyway, I'm here. Maybe I'm going to get a glass of water just to clear my throat.
Ah, well, then you must be preparing to reminisce.
So, David,
Yeah,
Louis is at home and he has some technical problems trying to connect. Can you start for us? And when he,
I was kind of hoping you would.
well, you see, I'm not as facilitated as all of you are. Because the seminar room.
Uh-oh.
Also, you do have more Amitsur time than I do.
True, that is true, but I wasn't, yeah, okay, I can start.
Louis might connect any minute, but we should start anyway.
Yeah. Hey, Lance, can you hear me? No,
You. David?
yeah, so
Who did
Alex,
you-
you made it,
Yeah, I made it long ago, actually. It was very fast.
good. So I think we are tasked with beginning to reminisce. I do not know how Louis intended to organize this, though he could connect at any moment. But why don't we just start by reminiscing? Somebody, Alex, I think you were thinking you might want to say something. Is that right?
Okay, I mean, I didn't expect to be the first one, but that's okay. I will be. I mean, I want to say something which is, I have some which I think has a moral lesson somehow. I started to say the other day that what I really took from Shimshon for a lifetime is is modesty and seriousness. It started already. He was one of the judges for my thesis, and usually this is kept secret. The PhD student who writes the thesis is not supposed to know who are the judges, the referees of his thesis. But Shimshon called me and say, look, I know that I'm not supposed to do it, but frankly, if I will just glance at it, I will not get anything out of it. Why don't you come to me and we'll sit together and go over the thesis? And I was, you know, it was clear that he's going to approve it, because not because it was so good and not because I was so good, but you know, I wrote it under Hillel Fürstenberg, which was his colleague. If he would not approve my thesis, it will be slash in the face, not to me, but to Hillel Fürstenberg. So, you know, let's be fair. Most of us, when we get such a thesis to check, we don't go to the details in red. But you won't believe, I met him twice for 2-3 hours, and we really went over the thesis page by page. You know, maybe not every little lemma, some lemma. I said, okay, this I understand. He really wanted to understand it. And not because it was so important, not, I mean, don't get the wrong impression. And not because it was in his area, because it was so serious, and he was serious about everything he was doing. And what I really miss is the seminars. I think with all my life, I try to copy the style of his seminar, not maybe with great success, because in his seminar, you know, he was sitting on the first line and taking notes, you know, listen to every lecture. It doesn't matter who is the lecture. There is always something to learn. And he would take notes if it will be an important professor or it would be a graduate student who will give the lecture. Amitsur was there taking notes, asking questions, wants to understand everything. And he created an atmosphere in this seminar, which was really outstanding. I learned so much because many of you probably remember that, you know, you could speak there. You know, it was a small room, not too many people. I mean, the audience could even stand up to the blackboard and ask something on the blackboard and something. We were really learning this way. And it's not accidental that when she passed away, so, you know, it was completely unexpected, we decided that the best way to remember him would not to call after him some buildings, some lecture rooms, something, but we call the algebra seminar at the Hebrew University is still called Amitsur Seminar. And somehow I think we still have the feeling that he's there with us. So this is really something that I took from him for a lifetime.
So Alex, I'm going to try not to talk too much, but I do believe you because he went through my thesis, and I do believe it was word for word going through my thesis. And I also believe he's the only one who did that. So you know, I had other readers, including Jacobson, but I believe that he went through it word for word. And I didn't remember that until you just said what you said. So somebody else.
I made some notes. Am I unmuted? Yeah.
Yes, I can hear you.
Okay, good. Of some of the things, not so much about Shimshon being a great mathematician and advisor, but some of the other things that Shimshon did. First of all, I want to just amplify a little bit about what Bob Guralnick said. Shimshon had many years ago, he would describe on first hearing of a result, it was wrong. Then you convinced him that it was right, but then it was due to Levitsky. And once when he was visiting San Diego, he was in a seminar with some of the students, and he said, he started this out. Now, I had informed students that it was like this. So Shimshon again began, it's wrong, then it's due to Levitsky, and the students started to laugh, and he said, why are you laughing? And we went on. It's just because Small had told them that this is what's going to happen. And it did. But there are some other things I'd bring up about Shimshon. Namely, I don't know how many people know that he had served for 3 years in the British Army. And once he was going over this at a meeting in Leeds, and he was talking with Alfred Goldie, who was, I don't know, being Alfred. But anyway, he told Alfred, well, you know, the fact that I'm bald is due to the food I had for 3 years in the British Army. And Alfred began to stutter, but we gave the forces the best food that we could. And then, proceeding in this sort of vein, Shimshon was on Mount Scopus during the siege in 1948, and the radio operator was killed on the first day. And the commander turned to Shimshon that, well, you're a mathematician, you've been up there. There's a library here. Learn radio by the end of the day, which he did, apparently. And he could always fix radios. It would help if he were under a little an extremis, but he did. He had this wonderful knowledge of what to do in various situations. I'm looking at some of my notes here, but I observed him once, a bunch of us did, on a Thanksgiving Day in 1977, it must have been, in Israel, where somebody's radio conked out or something, and they brought it to Shimshon, and he fixed it. right on the spot. It happened. He was willing to push a switch harder than anybody else was. And then the thing connected, but he had this wonderful way of doing, of just being able to handle any situation. And I think students and others around were always impressed by how Shimshon could do things under all circumstances. I'm just looking from some notes I made yesterday.
Lance, what was the gizmo he carried with him?
What?
The gizmo he carried with him, Lance.
Oh, he he carried with him a continuity tester, which is strange for a mathematician to look at whether or not some circuits were connecting or not. But I thought it was really pretty apt that here was this Algebras checking for continuity. But anyway, he could. Thank you, Don. But he visited San Diego a number of times and for extended time. And I remember hearing after the fact that he liked to go body surfing on Moonlight Beach in Encinitas while Sarah sat at and watched. But it was, it was just, he would do anything. Apparently he used to body surf in the Mediterranean as well. But
Smaller waves, though.
yeah, but he would follow the waves and would do it. And Sarah would usually sit and watch. But he had this amazing range of versatility. He also once remarked to a bunch of us that some of his best mathematics came from his mistakes. And he was particularly talking about the Amitsur cohomology at that time. But he had this one thing he was very serious about, of course, was his faith. And it illumined many things that Shimshon did. He was a great influence on, I see Avanom is here and Alex still, the lives of most of us who came into contact with him and were fortunate enough to do work with him as well. But as I said earlier, he had a wonderful sense of humor while being as serious an individual as I have ever met. But I think now I should probably pass to someone else who would like to say something.
So Louis, do you want to take over or?
Okay. So in that case, David, do you have any reminiscences you'd like to do?
Well, actually, since you're giving me the floor, I will later, but Claudio, since I spent a lot of, I used the Amitsur Procesi theorem a great deal. I was wondering, and I haven't heard you talking on this subject of him. I was wondering if you would have something to add.
Me, yes. Maybe, well, here I am, but you have to show me. Can you hear me?
Yes, we can
Yes.
hear you.
Yes.
Oh, but you can also see me, maybe.
Yeah,
You're in a little shadow, but we can see you.
Okay. Well, basically, I guess Amitsur was essentially responsible for my choosing the thesis, the PhD thesis in Chicago, because it was, I think the year was 64, 65, when there was this big year in non-commutative algebra at the University of Chicago. And Amitsur gave lectures on polynomial identities, which I found very interesting. And I started to think about it because I wanted to see how much one could develop some kind of algebraic geometry for non-commutative algebras. And it seemed to me that non-commutative finally generated algebras, what I called affine, would be the right start. So I remember a couple of things. The first thing, I think when I showed him that his construction of the free algebra modulo the identities of matrices is a domain, and you know, the famous theorem that is a ring of fractions is a division algebra dimension and square over the center. And then I had sort of this idea that one could describe this by generic matrices. So as Lance said, the first reaction that he had was, so now that's not possible, something like that. But then I guess quickly understood that I was right. And that was actually, I guess, somewhat something which changed a little bit the approach to PI algebras. And then the next what about you know, I guess our work, which was if I remember, because you take me a little bit by surprise, I think was on non-commutative Nussdorf. Again, I think once I came to him and I said, look, if you have a PI algebra which is simple and finally generated over a field, then it is finite dimensional over this field. And again, at the beginning, he didn't believe me. So then that was, I think, the start of that paper. Then I don't know, for my PhD thesis, I think he was not there. It wasn't, I don't remember if it was the next time or, but in any case, at some point I met him again in Israel. And what I really remember with great pleasure is the fact that on a Shabbat, he invited me and my wife to take a walk through Jerusalem, which is a city which I guess he loved and he knew very well. So, and since you know, I'm also from a city which is quite ancient with a lot of history, we had some kind of you know, amusing discussions, comparisons about the history of Rome and the history of Jerusalem. Then I think at this point I really do not have much more to add. Of course, I was quite impressed, and when he proved what I had tried to do and I had not been able to do, that is that the generic division algebras are non-cross products by some kind of generic argument. I had some ideas, but I was not able to pull them through as he did. I think maybe that should be enough.
Okay.
Okay.
Maybe Louis, maybe I would like to say something.
Sure.
Okay, thank you. It's I did not, when it was asked who wanted to speak, I did not say that I wanted to because too much to say, really. I happen to be Amitsur Shimshon, oldest surviving student. There was just one before me, like Shmuel Schreiber, and he has passed away quite a few years now. He was actually also one of my teachers, was a teaching assistant. And well, before I go on, I wanted to point out, because maybe not everybody noticed it, that two of Shimshon's children are with us here. It's יפה נעים לראות אתכם, חנה ואלי. Here they are waving at us. Excuse me, I lapsed into talk to say welcome them in Hebrew, that was all. But I mean, almost everything that people mentioned here making memories. Of course, Lenz talked as he liked always to mention that Shimshon always recalling Levitsky. And actually, I was also lucky enough to hear Levitsky for a couple of months before he passed away at the early age of 52. But then Shimshon took over his course. Yes, and also I think Alex mentioned the seminar that Amitsur was always taking notes from everybody's talk. And my impression was he was not so much interested in the result himself. I mean, of course, there are of interest, some more, some less. But he was very interested in the method of proof, what made it work, what was the idea of the speaker, how did he gauge these things. And because he thought that, probably thought that maybe he could learn something from everybody. I mean, when he regarded the people as his equal. I remember when I was still a PhD student, and he would talk to me as if I was his colleague in everything. I mean, many of the things he said that passed quite over my head. Things that I did not know yet or did not understand it, but he talked seriously as he was talking to somebody, one of his peers that was on equal footing with him. That impressed him. And I think somebody also mentioned that he was during the Second World War in the British Army, of course. And I happened to see some of his letters to Levitsky at that time, and they were about mathematics. If during the war, he found times to think about mathematics and write about it and do it. That was Shimshon. And I remember when I first came to him, said I would like to do a PhD thesis. He was not my supervisor at the master stage because he was on sabbatical. And my master thesis was group theory. And I wanted to continue with it. But Amitsur, of course, was more for, I mean, he knew group theory and he had some very remarkable, group theoretical results, but he would like to do something ring theory. And I think at that time, exactly, he got a thesis from Kaik, I think, and he gave me the thesis, maybe I should read it and see if I can do something. And I was interested in other things, but of course I took it. And didn't even look at it at the time when he talked. But at the evening at home, I thought, okay, my supervisor gave me this thing, I should look at it. I looked at it and it was written in Dutch. Not double Dutch, as there is a saying in English, but it was written in Dutch. And I came the next day and told Shimshon, well, it's in Dutch. I said, well, I thought maybe you could manage it. Well, I could not. So I put it aside and went on with my things. And after some time, I came to him and say, okay, I did go on with my own thing and I managed to do something. And I said, okay, if you already did something, go on with it. I mean, he would let people, not only me, do whatever they liked. I mean, he would give them a freedom. And not everybody liked it. There were some people who would like more direction, but certainly somebody like Aner. And I preferred this way, that we should be able to pursue our ideas. And of course, but he would correct us and tell us. And I remember once I came to him and said, well, I saw it for a few weeks, I did not get anything. I said, oh, that's nothing. I go around for months and don't get anything. That was encouraging. And one day, I came to him and full of it, there is Hebrew saying, tchilun rechimu. I mean, sort of fear and hesitation, and something, and ask, do you think I have enough for a thesis? And he said, of course you do. As if it was self-evident things. That's what I remember. That's really the time that I remember that my thesis was approved. Yes, after that, of course, after that, it took about a full year to write it. And Shimshon said about me about every word, really, through me. He guided through me how to write mathematics and so on. Very, very, very helpful. And of course, there were two other referees, but it was not easy to find referees. It was written in Hebrew, At that time, there were not many algebraists, and certainly not many group theorists in Israel. So, and I know for a fact, it's not a guess, I know that the other two did not read it. It was really only Shimshon who read it and approved it. So maybe I should not say so. Maybe I should not admit it. But I think by now I'm well after retirement. Well, I think I probably could go on and on finding things from here and there. Just like mentioned the tester, the electric tester that he always had with him, as was mentioned, because he was good at all kinds of things. He once repaired a writing machine, yes, or what's it called? A typewriter, yes, I forgot Yes, all kind of, he was very good. I mean, he was good at everything he tried, really. Okay, maybe somebody else.
Maybe I can say something. It's also related to what Avinoam said.
Sure.
Okay. It's kind of, I want to briefly discuss an incident when I brought, after some time of research, I brought to Amitsur a draft paper which I've written, and he took it and he said, okay, he will read it, and we arranged to meet a week afterwards or something like this. And then I came to his room and asked, what do you think? So he said, it's fine, it's okay. So I asked him, shall I submit it to publication? And he said, well, maybe you should give it half a year or so. And then I was a bit upset or nervous, and I said, what, did you find any mistakes? So he said, no, I read it carefully and there are no mistakes. And did you, maybe the results should be strengthened? So he said, no, just give it half a year. And indeed, I gave it half a year, and after half a year, it was a completely different paper. And this demonstrates also what Avinoam said. I think he had a very concrete idea what more could be done, but he didn't want to force his idea, or sometimes even to suggest. He wanted everything to come from the student. A little bit like Socrates in the dialogues of Socrates. He kind of delivered the kind of showed people that they can find the answers themselves. So in this sense, I thought that mathematical research is a little bit like a red wine. Sometimes it just needs time to ripen. And maybe just 1 minute, another memory. I remember that when I was a postdoc in Oxford, and he and Sarah visited us for a very beautiful day in Oxford, and they were also with two of their granddaughters, and I was also very impressed by the very such close relationships with the granddaughters, and all. I remember how they liked the botanic gardens and stuff like this. So this was another significant memory.
Thank you. Well, we have about 1 minute left. Actually, I'd like to say something about Shimshon and David. Maybe David will contradict that, but I remember several times David said, you know, Shimshon is 30 years older than I am, but anytime I visit him, he just completely exhausts me because he's always thinking mathematics and always insisting that we work straight through the day, try to do the best that we can. Isn't that true? Isn't that what you said?
A specific incident, that first paper we wrote. But yes, he would, more than that, we would work through the day, and at the end of the day, I'd have a headache because we'd been working so hard. That's what I remember about it. Anyway.
And my recollection is that he was so understandable. He took the most difficult things and just, as I think people mentioned this, I mean, he just broke them down, you know, almost like Beethoven. Like he just put them down into their most clear parts that, you know, you could understand the most complicated concepts. Anyway, that's, I think it's probably time to move on to the talks.
Maybe I think, Louis, I think the next talk is in 9 minutes or
9 minutes. Oh, so we could reminisce some more.
So I think that maybe if someone from the Amitsur family who are with us in Zoom, maybe, and also, you know, some other people, I think maybe it's better not to have a break and to have 9 more minutes.
Absolutely.
If it's fine. Yeah. So if anyone from the family, we heard wonderful things at the reception from Hannah,
okay, I'm willing to say something. My brother is on the way to Eilat, so he's listening to this from his car, so he probably can't speak and drive at the same time. So when you were saying that he was, 3 years in the military in the British, he got a degree of some kind of a radio technician, a little bit more of assistant engineer in radio. And then I told everybody he went to Holland and and developed some kind of a new gadget. And he had an appreciation letter from the Queen saying they're very thankful for his great inventions and so on. What it was, I don't really know because he never told us anything at home. And swimming, he lived in Tel Aviv, so he had the Mediterranean. And then when he was in the British Army, he was stationed at the bay in Haifa, and they did a lot of swimming there. Just for the knowledge, my mother couldn't swim. She was afraid. So that's why she sat and watched him surf. But he always said, do whatever you love to do when you study. Don't think of the economic part of it. Do what you love. Once you do that, then you'll get far ahead. And that was it's very important to us, knowing that we didn't have to do what he liked, but we should do what we like. And that isn't easy. Now, when I see my kids with him, he loved children. He really did. And he loved them when they were extremely young. And he loved playing with all these toys. He had an electric train. I don't think my brother wanted it, but my father wanted it so much. And he used to open and work with the electric train. And I think because he came from very poor beginnings, that he had nothing, that it was so important for him to play with us and do things with us. So, and no, when he was, the story was that when he was on Mount Scopus and they were sieged in, and my parents lived in a house which my father used to call the penthouse, which was actually one room there. And we found a letter saying, please come at Thursday between 2 and 3 and wear this certain dress so I can see you watching with my binoculars. So, you know, it was very interesting things to see. But I said it, and he didn't care whether we were great students or not, but he cared very much for us to respect our teachers and our elders. He says, you can be talented, you can be more talented, you can do this, but when you have a teacher, no matter what, respect him. And that was very important to him. And a lot of other things, but the time is short.
Yeah, there's some more time.
Well, I told everyone he loved Jerusalem because he was born there. And not only was he born there, his family came from Belarus mainly. And his mother's family came 1870, and his father came, his great-grandfather came around the beginning of the 20th century, I think first year, or sorry, the end of the 19th century, and he really loved the history of Jerusalem. One of the things that he really loved this country. And you were talking about his faith. I told the students, I told everyone that he participated in building two very important synagogues in Yerushalayim. Those who know it, the synagogue of Ramban in the German colony, and the one next to the president's home, Oel Nechama. And when I'm saying he was part of the founding people who built this, and I think he put many salaries into building these two communities. So it was very important to him. He was also a feminist. You know, it wasn't simple to be an Orthodox feminist at that time. We're talking, I'm 73, so just think when he was, and he was very angry that in school we learned how to sew and never learned how to fix any things at home. So he taught us how to, at least he taught me electricity, how to connect things, how to build things. And then whenever something was broken, and my mother said, well, Shimshon, fix it. He said, why did I teach your daughters to do it? Let them do it. So that was very important for him to, and not only that, it was important that we go to the army, which wasn't very common at that time. So, you know, we had other sides to him. And he made us every Shabbat, we had to learn the Torah portion every Friday night. After the meal, we had to sit, the whole family, and then learn with him. And as I said, because we were, he really came from humble beginnings. He came from a family that my grandfather said sometimes didn't have money for food to eat and so on Saturdays. So he appreciated everything, and he made us appreciate things. He wouldn't let a drop of water, you know, in drop in Ujjalai. He just couldn't stand it. He couldn't stand it if we didn't finish whatever my mother cooked. So all these things combined with his ambition, the more I read, the more I admire him. And when I hear you, I learn even new things. So
Thank you. Okay, well, I guess we probably should, start maybe in half a minute and at the regular talks. So thanks everybody for coming by and sharing your memories.
thank you.
Oh, Mia.
Very much. So should we start? Should we turn to Belov's talk now? Alexei Belov is going to speak on the Gelfand conjecture, and the method of proof of Specht's problem.
Okay. 1 second. Before 1 second, first of all, I want to, because it's 100 years old of Amitsur, I want to say that I met Amitsur, Shimshon, and his Sarah and Louis Rowan first time in my life in the 1991 in Barnaul. Maybe you remember it. That time,
yeah, of course.
During the Putsch time when he flight, everything was unclear, but Amitsur decided to fly to Barnaul, and that's the place where I met him. We had him, Sarah, Louis, offer others, and it was somehow nice time for me, and it was nice conference. Although very specific one. Maybe you remember. So this is my memories on Shimshon. I even have some photo. Maybe I will sometime print it and send. Okay. Let me start talk. Somebody said, for example, once Amy Brown, that the PI theory, he said very suspiciously died. However, I completely disagree with it. No, not because just of talk of on the results of Aner Shalev, and we have also talk of but also there are some nice paper for using Sergeyev algebra in advances of Alan Berle. We have also some paper, there is some new insight of Zelmanov or Propi group related with the PI algebra, and it is also connected to mainstream. And there are many, there are other stuff. No, of course, I know very nice paper of Claudio Procesi about the geometry of polynomial identities. No, he published it in the Известия of Russian Academy of Science. And there are a lot of books related with invariant. No, I'm not talking just about our book with Louis and Uzi. So the life is continuous, and the PI theory provides something implicit. Let me mention a part of this, some results Uzi and Galdor about what is the Grassmann algebra or sign minus in characteristic 2. It's also somehow it looks strange. What does it mean, sign minus in characteristic 2, and how to build Grassmann algebra? We had a paper in Transactions of American Mathematical Society, and this paper provided some way how to build superalgebra on some bad rings and suspicious rings, and how to provide Grassmann algebras. But this was originated in the Specht problem and in construction of infinitely based varieties over characteristic 2. So this is one issue. Another issue which I want to say is that Anton Haroshkin is planning to move to Israel. Of course, he's thinking at least about of that. So before all of this, let me come to the subject of talk. There are two methods of talk, of proof of Specht problem. One method is coming from Kemmer. Another method is coming from Grishin. Unfortunately, he passed away because of in this May because he was against vaccination. But there is another method to prove that any set of finite basis properties, and this method of proofs provides some relations combinatorial with Gelfand conjecture. Let me try to share the screen. Let me try to share screen. This is one issue. This is the paper about Grassmann algebra over arbitrary rings and the minus sun in arbitrary characteristics. That's about one relations. So the PI theory is a rich enough theory. This is Berele. And now let me talk to, this is joint work with Anton Haroshkin and Ivan Vorobyev. Do you see my screen?
Yes, yes.
So let me formulate the main result. Consider, let Wn, sorry for strange slides, it's more or less my first time seminar talk on the Zoom. Let Wn will be a Lie algebra formal vector field, and let's consider Lie algebra of polynomial vector field. The Lie algebra of linear vector field is denoted this way. We have the following decomposition of GLN models. So, in fact, we are interested in Lie algebra of vector fields who are 0 in 0. These algebras of finite codimensions are called the basic subalgebras and denoted LD. With each irreducible GLN representation, one associates the irreducible L sub 0 model with trivial actions on the algebra, and there are reduced models. Billion and models. Tau lambda is and for Lie algebra, and consider action of polynomial vector field on the models of tensor field. And the conjecture of Gelfand is for all k. And then the continuous cohomology as well as the Lie algebra homology are finitely dimensional over all k and lambda. And for any collections of weights, the tensor product for models are Noetherian L0 of n models. It means the tensor representation of polynomial vector field with 0 in 0, any tensor representation, are Noetherian action. That's their somehow mainstream theory. But of course, you cannot know such smart words. I like there is a Winnie Pooh, some person in the English book. I like much smaller. Consider polynomials of two variables. Now let's discuss on it's true for any amount of variables, but let's look on the two variables. You can have a following operation. Suppose there are you have polynomials P1 and P2. You can make linear combination and substitution. Note that I is polynomial of one variable. And you have this substitution. Instead of x, you substitute polynomial of x. And instead of y, you substitute polynomial of y. So you have linear combination and this type of substitution. Same question can be done for any amount of variables, x sub 1, x sub k. But for simplicity, I just discuss x and y. And what I can say, is it true that every system of polynomials can be deduced from finite subsystem? And same question for positive characteristic. I want to comment that in fact, the proof of this combinatorial question implies, as was noted by Horoshkin, Gelfand conjecture. So all of this stuff, in fact, this combinatorial fact, you have P1 for any set, for any amount of variables. Let me comment it. If you have positive characteristic, any characteristic, if you have just one variable, then every system can be finite based from finite subsystem, can be deduced from finite subsystem. You don't have any characteristic restriction if you have just one variable. If you have two variables, then for any positive characteristic, there exists an infinite based set of polynomials. That's the fact. And if the characteristic 0, then for arbitrary number of variables, every set of polynomials are finitely based of all of these systems. That's the situation in which we are. So, in fact, proof of this combinatorial fact implies Gelfand conjecture. So, this situation with this combinatorial fact, if number of variables is 1, everything is finitely based, number of variables 2 or more, then in positive characteristic is infinitely based situation. If number of variables is, if characteristic is 0, then it's finitely based. That's the situation. And let me show on the very end, it's related to Gelfand conjecture, but it shows that let me show this is infinitely based system of polynomials. P is a characteristic of ground field. And these constructions looks pretty similar to Grishин and Shigalov examples of T-space. So this set of polynomials respect to K is infinitely based in positive characteristic. No, there are some proof of it. I have not very fancy English text, but at least it was, and the proof is somehow looks, it's really, proof looks, it's pretty similar to the counterexamples of Specht problem in positive characteristic. But even you don't need anything about Specht. You just prove that this set of polynomials is infinitely based. By the way, modulo x minus y square. Even such, so it looks like Grassmann. This is one comment about positive characteristic. No, it means that Gelfand conjecture but Gelfand conjecture is for characteristic 0. What happened about this polynomial set of substitutions? Of course, it's all ideology is well understood if you have just two variables. And what is the structure of proof of all of this? First of all, we consider not just finitely based, but regular finitely based. First of all, we consider homogeneous operators and homogeneous parts of all of these operators. That what we do. First of all, we substitute instead of we make some substitution. Instead of xi, we substitute xi times 1 plus t, and then we separate parts from t. Then some t goes to x, some t goes to y. And we need to prove necessity separately from x and separately from y. We have a right to multiply on some variables VIC, and we have substitution into remaining variables. If we pretend that we don't have substitution goes just for x, then everything fine. How it's also y. We pretended and we play some on the fact that when we subtract, we just get more y. But if we have t such that you can multiply by y, so we drop down the y-ness of all of this stuff. In fact, it's some differential operator. It's due to lack of time. I want to say that there are some the stuff is following. First of all, we multiply by 1 plus t x, and then we make some sort. T goes to x1 to x2 and xn. If you have notoriety of every type of term, we have global notoriety. It's one idea. Second idea, when we have t such that VIT we substitute polynomial of x sub 1, then we got and we have usual substitution. Then we can consider another substitution who does not hit x sub 1, because the diff, if you have finite basis respect to 1 and respect to second substitution, the difference will provide terms with low degree by y by higher degree of x. This is stuff how it goes. In fact, due to lack of time, I cannot get through all the details. But what I want to say is that when we do structure approach like Kemer, it's nice, but sometimes it's reasonable to have different type of proofs. And different type of proofs provide different abilities. For example, this pure combinatorial approach is somehow is better to generalize, and this provides solution of Gelfand conjecture. I just put this talk a few days ago, but we shall write a paper about how Specht problem, and this approach originated by Grishin. By the way, that method implies Gelfand conjecture was noticed by Anton Haroshkin. mainstream, homology, and so on, the model consequences. And this question was open for a long time. So I want to say that I'm happy that Amitsur was the founder of PI theory. And because of his foundation of PI theory, it has a good, nice relations from mainstream problems. Due to lack of time, I just want to point it out, but I think I will have more detailed talks on the other seminars. So, and I'm happy to be on the conference, and thank you for listening.
Thank you very much. Are there any questions?
I see question of Berle. I want to say that when we finish a paper, I shall send to him because I would be happy to send.
Mm-hmm. Okay, well, thank.
Send it to me also.
Sorry.
Okay, well, we're looking forward to further details. And thank you very much. So the next talk is by Eugene Plotkin, Geometric Equivalence of Algebras. Oh, can you unshare the screen, please?
Yes, sure.
Is Evgeny there?
Yeah, I did it.
I'm here, just a moment.
Okay.
So can I share already? Yeah.
Sure.
Mm-hmm. Here it is. Louis, can I start? Louis, can I start? Can I start?
Sure, sure.
Okay. So the talk will be about geometric equivalence of algebras. But first of all, I want to say that it's a pleasure to be here and to remember Shimshon, because in fact, meeting with Amitsur and Sarah many years ago in Barnaul, it was during the very, very, dangerous days of I don't remember the month, 1991, during the coup, and he, in a sense, determined what happened afterwards, and we moved to Israel, and we felt all the time that his generous attitude to what's going on, and we're very grateful to Shimshon, and we respect very much what he did for us. So because of that, I have chosen the topic which somehow is related to the interest of Amitsur, and this is geometric equivalence of algebras. So this is a joint work with Lena Ladova, my father, and Arkady Tsurkov and Grigory Zhitomirsky. In fact, there is a team which we are working together on that many years, and all started from the work of my father in 1996. And in fact, it was, the seminar, Amitsur seminar in Jerusalem, and what was discussed there is the geometry of a free group in concern of Tarski problem. And it was discussed the Makanin-Razborov approach, how to describe the solutions of equations there, and the notion of the radical appeared, and so on and so on. And as far as I understand, as far as I remember, this, a set of questions related to a free group, basically to a free group, maybe in some sense stimulated my father to start thinking about the geometric approach to algebras in general. So today I will touch one of the questions which are in this area. So the setting is as follows. So suppose we have a theta variety of algebras. So we take a set of variables x1, xn, and the w of x is a free algebra in theta. Let's take an algebra H in theta. Consider the rule H1 as H2, two algebras in theta. And Hn is to the n is a Cartesian power of H. It will be an F space where all algebraic sets lie in the future, in the sequel. So it can be also considered, and it's a very, very fruitful point of view, as a set of all homomorphism from the Wx to H. So it's not on the place. Okay, so the main question behind all further considerations is as follows. Suppose we have two algebras equipped with a sort of logical description. What can be said about these algebras? How close are they? So in fact, we can move in two directions, in purely model theoretic directions, and ask about elementary equivalence of these algebras and look for the situation when elementary equivalence provide an isomorphism, which is quite popular subject now in nowadays, last years, and so on, for linear groups and so on. But we can look at the other directions, more geometric. So when two algebras have the similar possibilities with respect to solutions of equations. So, and this is the first question. And the second one, when the coincidence of logical descriptions provides an isomorphism between algebras in question. So today I will dwell on first one, because, and before I will go to the details, I have to say that this is the point of how to connect syntaxes and semantics in general, the point how to connect logical formulas and their values, which are purely geometric objects, the definable sets. So let's take for today just an equational case. So the model situation is the algebra, it's naive in a sense inside on algebraic geometry. So we suppose we have an algebra of polynomials, commutative, associative, whatever, everything is fine. And we consider some now a set of polynomials, f1, fm, and we're looking for solutions of these polynomials. So we have a set of polynomials, we have a system of equations, and we take the points which lie in the F space, and then we are looking for A. It's not radical. The A is the set of all points which are solutions of T. And then we go back upstairs and consider all consequences of T, which is in fact the radical of T, which is exactly the set of all solutions having the same set of all formulas having the same set of solutions. So this used to call the radical, and Hilbert Zans described this radical in very beautiful way in the case when our field is good enough. So we want to imitate this Galois correspondence in the general case. To do exactly the same for any variety of algebras. So this is the special variety of commutative algebras of the K. And now we want to imitate the same for any variety of algebras theta. So instead of K of X, the algebra polynomials, we have to take the free algebra, a free algebra in this variety. Then we take a set of equations, which is in fact a subset of T times T. So set of equations where the elements are just elements of a free algebra, fixed one, free algebra. And then we take the F in space, which should be, in order to take an F in space depends on algebra, where we are, and we take an algebra H and consider the F in space H to the N. And then we are taking the points, such that these points are solutions of this system of equations in the very, very usual way, which means that we substitute instead of variables here these points, and then we get the equalities. And then we do exactly the same what it was before. We go upstairs and consider all equations which are have the same set of solutions. It's also the radical. And the difference is that we are in the general situation. Nobody knows how the radical looks like. So it's very difficult to describe it. But we know that syntactically, the radical is exactly what can be deduced for the given set of equations. Exactly what can be deduced. And how it can be deduced via the geometry, it follows from this Galois correspondence. So the correspondence of these arrows can be thought like arrows back and forth from the logic to geometry and from geometry to logic. And I would like to emphasize very several times that every question that we can formulate in the terms of logic can be formulated on the level of geometry, and vice versa. Every question of this level, which is formulated here, can be translated on the language of equations. And this is just the usual correspondence between the closed objects in Galois correspondence. So we want to compare algebras. So let's take a system of equations T, and we take two algebras, H1 and H2, and construct F spaces. And then we consider solutions of this system in equations in each of them, T prime H1 and T prime H2. And then we want to compare this algebraic sets, but it's difficult to compare it on the level of geometry. We go upstairs and we construct a radical, a closure of T with respect to H1. And then we construct the closure with the H2. And then we compare the closures. So we say that two algebras, H1 and H2, are called geometrically equivalent if for every set X and every set of equations T, the Galois closures of T with respect H1 and H2 coincide. That's a very beautiful definition on my opinion, because it reflects the idea of coincidence of geometries in a very precise way. So the geometry of H1, H2 really the same if we have such kind of coincidence or such kind of equation of equality. T prime radicals should be the same. How to check this? It's how to check it. It's good that we can do it. So the theorem, the fact states that algebras H1 and H2 are geometrically equivalent if and only if they satisfy the same infinite quasi-identities. I remind that quasi-identities is expression of the form, this form W1 is equal to W1 prime, blah, blah, blah. WS is equal to WS prime, and we can continue the sequence, implies that W0 is equal to W0 prime. So I should pay attention that we need infinite dimensional, we need infinite quasi-identities. So fortunately, there is a Birkhoff theorem which describes how to construct an infinite quasi-identity and the infinite quasi-variety. So in a way, we can say that two algebras H1 and H2. I forgot to say that from the very beginning, we assume that they generate the same variety. So two algebras H1 and H2 are geometrically equivalent if and only if the infinitary quasi-varieties coincide. So we have such a understanding what we can say about geometry of these algebras. And it was a question, what means it's infinitary, and for immediately the notion of geometric Noetherian or Noetherian by equations algebra appeared. So we say that that algebra H is geometrically Noetherian if there exist defined subsets of T such that the radicals of with respect to this subset and the whole radical coincide. And it was used many times in the case of free groups, that every linear group is geometrically Noetherian, and this is clearly implies that a free group is geometrical Noetherian, and this means that we don't have infinite systems of equations over the free groups. But basically, this was the unique case when we know that something is Noetherian. Basically, it was the situation till the work of Romanovsky. It's fantastic proof that he proved that every free solvable group is geometrically Noetherian. And I should say that free solvable group is not a linear group. Nevertheless, it's still geometrical Noetherian. And there is this is the unique example of such kind up to now. And the huge open problem, what can be said about geometric Noetherianity of free associative and free Lie algebras? Are there infinite systems equations on these based on these algebras? It was several attempts to get the proof something for Lie algebras, and these problem looks very, very difficult and far from being close to some understanding solution, whatever. So this is the free open question in the sense of algebras. Okay, then I go to the details, and then I have such a setting that let theta 0 be the category of free algebras. And we have a category of algebraic sets. So we take all algebraic sets like objects and rational maps, which can be defined with respect to any category as a functors. And C theta of H is the dual category of closed congruences. So we have these two categories which are dually equivalent. So it's clear that if two algebras are equivalent, then the categories are isomorphic. So the question, what can be said in the opposite direction? So there is a theorem which is just a particular case of general situation, which I want to show the following. So suppose we have two algebras, and we consider the following varieties: the variety of groups, Jordan algebras, inverse semigroups, and variety of nilpotent groups of class D. So the categories of algebraic sets are isomorphic if and only if H1 and H2 are geometrically equivalent, which means that the arrow here is goes in two directions. What happens if we take the variety of commutative algebras or Lie algebras? So take an automorphism of the ground field, and we can define a new multiplication. So we change the signature of algebra. So what happens that the categories H1 and H2 are isomorphic if and only if the twisted with respect to the sigma algebra H1 and H2 are equivalent. The similar situation are geometrically equivalent. The similar situation for associative algebras a bit more complicated. And this situation hints out the following definition. Morita type definition, which is very, very familiar to everybody. So we call algebras H1 and H2 geometrically similar if the categories of algebraic set H are isomorphic. So we consider these categories are like an invariant of a geometry of H1 and H2. If we know that if they are equivalent, they are trivially geometrically similar. What can be said vice versa? Here, I need 2 minutes. Here, the notion of automorphism of the category comes to play. So we define the internal inner automorphism of the category of theta 0, category of free algebras. Inner automorphism, which is isomorphic as a functor to identity automorphism. And we immediately come to the understanding that if all of the automorphisms are inner, then we have two algebras geometrically Morita equivalent or geometrically similar, if and only if they are geometrically equivalent. What happens in the general case? We consider the group of automorphism. This is out of theta 0 modulo in automorphism. And this is the group which is responsible for geometry, for non-trivial deformation of geometry, which preserve the geometrical properties. And this is beautiful object. And Arkady Tsurkov described this group and some Grigory Zhitomirsky. So there is some now insight on out theta 0 when this out is non-trivial. When it's non-trivial. For groups, recently Tsurkov and Barbosa constructed a very beautiful variety of groups which possesses an automorphism. It's first example of a highly non-trivial variety of groups which possesses automorphism. And I have no time, just I formulate the final theorem. So two algebras, H1 and H2, are geometrically similar, if and only if H1, H2 sigma are geometrically equivalent for some sigma pro out theta 0. So in very plain words, this means that what can we do with the algebra to preserve geometric properties? So suppose we have H1 and H2 geometrically equivalent, and we want to deform H2. So what is allowed? So allowed two things: to do the operations which are allowed inside the quasi-variety. For example, H2 and H2 times in squared have the same geometry. This is because of they generate the same variety. And also we can change the signature of this algebra, define new operation, and the new algebra will be in the same variety, and the initial algebra and the new algebra with respect to this new operation will be geometrically equivalent. And this means that basically, this means that the group of automorphisms of the category of free algebras has outer automorphisms. And this is the main result, and just a flavor what's going on. And it will be nice to get a general theorem to understand when there are such automorphisms, what a meta-logical situation in this case. So, and I want to finish with just words that all these things which I described in the case of equational geometry can be extended to logical situation, to consider instead of equations logical formulas. And then we have questions very, very similar to the questions of elementary equivalence of algebra, which are quite typical for model theory. Thank you very much.
Thank you. Thank you very much, Evgeny. I think we should probably move straight on to the next talk, so to try to keep on schedule. So that was so the next talk was supposed to be given by Leonid Bokut, Grobner-Shirshov basis theory and word problems for metatrivial Poisson algebras, but I think Professor Bokut is indisposed, so his colleague Zuri Zhang is going to give the talk. Thank you.
Thank you. But I cannot share the screen.
Oh.
Because it's not allowed.
Wait, how? Can I do something about that?
Can you permit my sharing or something? It says that
I think Shai can do it.
It's really very interesting how you get this general geometric view of algebra.
I think the open field, which is maybe difficult, is associative at the algebras. The figure out what really goes there, and maybe other non-associative algebras, I don't know. And it reminds a bit the situation for groups and algebras in model theory, because in model theory there are many open problems for these algebras which are solved for groups. That's what I wanted to say.
Okay, so I see that Zhang has been able to share the screen now.
Yes, thank you. Yes. So should I begin?
Yes, please.
Yes. Thank you for inviting Professor Bokut to give a presentation here. But unfortunately, Professor Bokut is ill today, and because of some COVID-19 case, he was once get the COVID-19 and now has some effect still. So he asked me to help him to give the presentation here. And the slides are basically prepared by Professor Bokut. So his talk is on Grobner-Shirshov basis theory and word problems for metatrivial Poisson algebras. A Poisson algebra is an algebra with two operations. One is dot and the other is a bracket, this Poisson bracket. And the dot is commutative and associative operation. The Poisson bracket is a Lie product. And they satisfy the Leibniz identity, which means that the adjoint X is a derivation. Then any Lie algebra is a Poisson algebra if we define the dot operation to be trivial. A Poisson algebra is called metatrivial or metatrivial if P is an extension of an abelian Poisson algebra by another abelian ones. And by abelian, we mean that any product of the product of any two elements is zero. Our main result is a competition diamond lemma or equivalently a Grobner-Shirshov basis approach for metabillion Poisson algebra. So here we call metabillion or metatrivial, we call them the same. And this definition of metabillion is similar to the case of metabillion Lie algebra or metabillion Leibniz algebra and so on. This new result also gives a new composition diamond lemma for metabillion Lie algebras. So our method also works for metabillion Lie algebras. And our way is in some sense more simpler than the previous article. Using the composition diamond lemma for MP algebra, MP short for metabillion Poisson, and we have the following results. We can prove the Hilbert basis theorem for metabillion Poisson algebras, which means that if MP algebra is finitely generated, then it is finitely presented. And the word problem for every finitely presented MP algebra is solvable because we can prove that they have finite Grobner-Shirshov basis, and it will follow that the word problem is solvable. And we can also offer an algorithm for recognizing automorphisms of finitely generated free metabillion Poisson algebras. And using Grobner-Shirshov basis to recognize automorphism is not a new idea, but our proof is sort of different to the case of commutative algebra. For commutative algebras, they introduce some new letters, but for the case of metabillion Poisson algebra, there is no need to introduce new letters. And it also gives some new results for metabillion Lie algebra. We know that Ulrich Bethlen proved that the word problem for every finitely presented metabillion Lie algebra over a finite field is solvable. And we prove it for any computable field, which is not necessarily finite. We begin with a linear basis of a free MP algebra generated by X. And we use this notation with a subscript L to mean that the bracket is from left to right. And here we only use Poisson bracket. Then we can construct a linear basis which depends on the characteristic of the field. So if the characteristic is not 2, then it contains y1 to y4. Here, y2, y3, y4 only contains some monomials of small length. So their length is at most 4. And for y1, it's exactly the linear basis for free metabillion Lie algebra. So from here, we can see that metabillion Lie algebra and metabillion Poisson algebra are close in some sense. And then in order to introduce the Grobner-Shirshov based method, we need a well ordering. And for a monomial in the basis, by PBW, we mean the number of Poisson brackets that involved. And by ALU, we mean the length of U. That is the number of letters that appear in U. And then for a monomial, when we compare two monomials, we first compare their length, and then we compare the Poisson bracket. Then if these two numbers are the same, then we compare the letters from left to right. By this way, we can introduce a well ordering on the linear basis. And with respect to this ordering, by S bar, we mean the leading monomial of S with respect to the above ordering. Then when we deal with the Grobner-Shirshov based method, we are trying to deal with the elements in the ideal generated by a set. So here we will deal with the ideal generated by S. And we would like to see some elements in the ideal whose leading monomial is easy to write down, and we call them normal S polynomials. Every element in the generating set is called a normal S polynomial. And if an element in the generating set is of the leading monomial is of big length, so at least 5, then we can also define something like this called a normal S polynomial. Here we just multiply some letters from left to right and using the Poisson bracket. This one is similar to the case of commutative algebra. And the following part is trying to explain the leading monomial of the normal S polynomials. It just says that it's easy to read the leading monomial of such a normal S polynomial. But for some other elements in the ideal, sometimes we cannot know their leading monomial. For example, the following four kinds of polynomial. For the following four kinds of polynomial, their leading monomial has nothing to do of that of S. So in this case, we introduce something called multiplication conditions. And if all the multiplication conditions are trivial, which means that all such polynomials can be written as linear combination of normal S polynomials with smaller leading monomial, then every element in the ideal can be written as a linear combination of normal S polynomials. So we can written everything in the ideal as something like this 1 and 2. And by this way, we can write, we can have a feeling that this ideal, when we deal with the idea of a metatrivial Poisson algebra, it should be similar to the case of commutative algebra. And so we also define some general composition. The first one is that if the leading monomial are the same, then we consider the difference. If they are of the same form, then we first consider the least common multiple in the commutative algebra, and then we define something similar to the case of commutative algebra. So these are only three kinds of compositions, which is much less than the case of metatrivial Lie algebra in the previous paper. So the composition diamond lemma says that if we have a set and it's trivial under conditions, and which means that the certain polynomials can be written as a linear combination of smaller normal S polynomials, then the set is a Grobner-Shirshov basis, which means that every non-zero element in the ideal, the leading monomial is a leading monomial of some normal S polynomial. So this definition is not easy to see whether, by this definition, it's not easy to see whether a set is a Grobner-Shirshov basis. So in fact, we usually use 1 to check the conditions. And then if we can find a Grobner-Shirshov basis, then the set irreducible as, which means that all the monomial which is not a leading monomial of some normal S polynomial, then it will form a linear basis. And by this composition diamond lemma, we can prove that every finitely generated metatrivial Poisson algebra has a finite Grobner-Shirshov basis. In particular, it means that if it is finitely generated, then it should be finitely presented. And we can also show that the word problem, it also follows that the word problem for an arbitrarily finitely presented metatrivial Poisson algebra is solvable. Because we have a finite Grobner-Shirshov basis, then we can reduce them if they contain a leading monomial. This is quite similar to the case of commutative algebra. And then we can also use this composition diamond lemma to recognize automorphisms of free metatrivial Poisson algebra if it is finitely generated. And for a polynomial, we can separate it into two parts. The first part is every support is of big length is at least 2, and the other part is the linear part. So we use F2 to denote the nonlinear part and use F1 to denote the linear part. This is just notation. Then we can have the following theorem. If we have a finite set and we have an endomorphism of the free algebra induced by this one, we map Bi to its image Fi, and here is finitely generated. Then in order to see whether this endomorphism phi is an automorphism, we should study the following. We define a linear map phi tutor is an endomorphism of the subspace Kx. So the space spanned by the generating set. And we just map Bi to the linear part of the image of phi Bi. And then we can show that if phi is an automorphism of this free metatrivial algebra, it is equivalent to that the following two. If and only if the following two conditions hold. The first one says that phi theta is an automorphism. Well, this is a natural condition. And the second one says that the nonlinear part of the image should lie in the ideal generated by this set. So instead of studying the subalgebra generated by the image, we consider the ideal generated by such elements. And the Grobner-Shirshov basis deal with the ideal, and we can show that it has a finite Grobner-Shirshov basis. So the second condition is recognizable. We can recognize whether the nonlinear part of this image is lies in the ideal. And the first part is also recognizable. So it follows that there exists an algorithm for recognizing automorphism of the free algebra. Well, sorry, I speak it very fast, and then the time is good, I think. Thank you. Thank you very much.
Thank you. Thank you very much. Are there any questions? Okay, well, thank you for an interesting talk, and we probably should continue, right?
Thank you.
Is Miriam here?
Here.
Yeah.
I'm here.
Okay.
I have to just share the screen as Sarah has told me how to do that. Host disabled participant screen sharing. Why? Okay. I'll do it again.
It should be okay in
a minute.
Soon. Yeah, as long as the IIS people make you a co-host, Shai or Anat, then you will be able to share the screen, and probably in a minute it will be done.
Okay.
I mean, every speaker, it's another procedure to do it from or her own.
So, what? What do?
Shai, can you make Miriam Cohen a co-host?
Hi, yes, I have. She is a co-host.
Okay. So
try it again.
Try it again. I don't see the share screen. Where did it go? I don't see it.
Under more, sometimes.
Under more.
Yeah.
Share screen, yes.
Yes.
Good. Okay. Okay. Okay.
Great.
So,
okay.
Everything is okay now?
So
thank you, Anil.
Miriam Cohen is going to speak about representations of the quantum double of quasi-triangular Hopf algebras. Please.
Thank you very much. It's really a very great honor to speak in this important conference for Amitsur. I have a lot of that told already in the last reminiscence session. I just want to tell you about how Amitsur was extremely nice to me. And he was the first one who told me about Morita equivalence in Hopf algebra settings. And it was one of the most important topics that I ever wrote about. So I'm eternally grateful to him. The topic of this lecture was already discussed in a meeting that we had several months ago, honoring Amitai Regev and Dawn Zeilberger. So I apologize to all the people who will hear some of the things or most of the things twice. But As I remember, Louis was there and Malka was there, so I hope this is not going to be too much for you. Representations of the quantum double of finite groups are classified, while very little is known about those for general finite dimensional Hopf algebras. This research that I'm going to discuss here is an attempt to shed some light on this question. I will start with some general definitions and results that we are going to use. Semi-simple Hopf algebras over algebraically closed fields of characteristic 0 are the ones that we are going to look at, and they have an elusive nature. On one hand, they resemble finite groups in many aspects. As a result, many of the techniques in dealing with Hopf algebras try to use methods of group theory and the representation theory, and sometimes with a great deal of success. On the other hand, many elementary facts about finite groups are no longer true or hard to translate, or sometimes even false. So a common key feature of groups and Hopf algebras is that the tensor product V tensor W of two H modules or H representations become an H module in a non-trivial way by using the co-algebra structure of H. This resemblance is even stronger when HR, the R in question here is an element of H tensor H, is quasi-triangular. In this case, V tensor W is isomorphic to W tensor V using the R matrix. This, in a certain sense, is the essence of being quasi-triangular. Throughout, H, mu, delta, S, E, those are the structure maps, is a semi-simple and hence finite dimensional Hopf algebra of dimension, which we'll call D, over an algebraically closed field of characteristics 0 with multiplication mu and co-multiplication delta. Delta of H, here we use the very old Sweedler notation, is written as summation H1 tensor H2. The antipode S from H to H is the same as in groups, G goes to G inverse. This is really the basic resemblance. And an augmentation map epsilon from H to K, which is similar as for groups. When H is a Hopf algebra, we can twist the multiplication or the co-multiplication. For example, H cop is the Hopf algebra with co-multiplication delta cop of H, which is just summation H2 tensor H1. Its dual vector space H star is a semi-simple Hopf algebra as well, where here the delta of the H star is just the star of the mu of H, and the mu of H star is the star of the delta that belongs to H. The Greenfeld or quantum double of H, D of H, which was one of the big breakthrough in Hopf algebra theory by Greenfeld, is the tensor product algebra H star cop, the cop I've mentioned before, tensor H, with induced canonical Hopf algebra structure. D of H is also quasi-triangular via the image of the identity under the isomorphism hom HH to H tensor H star. The co-multiplication of D of H is simple. It's just the tensor of the respected co-multiplications of H star cop and H, while the multiplication, that's a more complicated issue. When H is semi-simple, it was proved by, I think, Redford, that so is D of H. We denote P bota H, a typical element of D of H, where P is in H star and H is in H. When applying the double construction to K of G, with PG, the G's projection, the projection to the G component of an element in Kg as a basis of Kg star dual to G. And then we have PH bow tie G times PH prime bow tie G prime is just delta of H G H prime G inverse PH bow tie G G prime. Here the multiplication is in the double is simpler than it is in a regular Hopf algebra. Two-module structure play a central role in this context. H is a right H star module via the hit action, defined as we see here. P applied to P hit A P prime is the same as A P P prime. And H is also a left H module via the adjoint action, which is similar to the adjoint action for groups. But in groups, H1 and S of H2 is just G and G inverse. So it's really an adjoint action, a generalized adjoint action. The combination of the two actions makes H into a D of H module via P bow tie H bullet A is first you apply H to A by the adjoint, and then you hit it from the right by S of P. This bullet action makes H into a D of H representation. Now, for every representation, V, a character chi V is defined as for groups to be the trace of rho V of H. The product of two characters is given as for groups chi V times chi W is chi V tensor W. And the product of characters is an integral sum of irreducible characters of H, same as for groups. We define the character algebra R of H to be the subalgebra of H star generated by the characters of H. It turns out that R of H is the algebra of all co-commutative elements of H star, that is delta X is delta cop X. When H is quasi-triangular, then RH is very nice. It's commutative. And not only is it commutative, but it is also semi-simple when H is semi-simple. So RH has a really nice form. It is a semi-simple commutative algebra for quasi-triangular Hopf algebras, and that's the situation we are going to be in. We'll take a V0 up to Vn minus 1, a complete set of non-isomorphic irreducible H modules of dimension di. Each one has dimension di. And the associated central primitive idempotent and irreducible character of H are chi 0 to chi n minus 1, where chi 0 is epsilon, the augmentation. Let lambda be the idempotent integral of H, and little lambda be the integral of H star satisfying lambda lambda equals 1. And we have lambda has the following. It is really the character of the multiplication map, and it's summation di chi I. When RH is commutative, and it is also semi-simple, as we know, it has also a basis of primitive orthogonal idempotent Fi, where F0 is 1 over d lambda. And now we come to the first definition that Sarah Westreich and myself have in a paper some years ago, the idea of a conjugacy class for Hopf algebras. It's Fi, where Fi, remember, is one of the primitive idempotents in R of H, and the FIH star applied to lambda. We have a theorem which relates this.
Okay, so I think that the basic theorem is that each conjugacy class CI is an irreducible D of H module via the action bullet that Mia mentioned in her lecture. So this conjugacy classes are the irreducible D of H modules, and they are not only the D of H, the irreducible D of H modules, but H is a direct sum of these D of H modules, and they play an important role in the representations of D of H. So class sums are also generalized, but instead of taking, as for groups, taking one group-like element from the conjugacy class, here we take like the normalization of all the group-like elements of the conjugacy class, and we refer to this eta I as the normalized class sum. We have that Fi and that I are dual basis of RH and C of H, and these definitions boil down to the usual ones when applied to finite groups G. So maybe I will skip it so that we will have time to go to our main results. So I just can assure you that these definitions boil down exactly to the definitions of conjugacy class and the conjugacy sums for H algebra, for groups algebras. When H is quasi-triangular, then we have a special case that R of H is commutative. And as was mentioned at the beginning, quasi-triangular Hopf algebras are very much like groups, so we have even more. So first I would like to mention that we have two Hopf algebra maps from H star cop to H and from H star op to H, and the Greenfeld map FQ of P. But what is most important for us now is the map phi from D of H to H. It's a Hopf projection from D of H, from the double to H. Hopf projection, it means it's an algebra projection and a coalgebra projection, and it's dual, of course. Hopf injection is from H star to D of H star. And why this phi so important for us here? It's the fact that every H module is now a D of H module via phi. And in particular, if Vi is an irreducible H module with associated character chi I, then it is also an irreducible D of H module with associated character phi star of chi I, which is then a character in R of D of H. So this map phi and phi star connects, is the first connection between representations of H and representations of D of H. Now, just notations, because it's confusing. So in order to distinguish between H and D of H, we use the following. Elements of D of H, we will usually pair with this hat. And the characters of D of H are with hat. Everything in D of H is with hats, while in H is just as usual, with the indices ups to avoid the confusion. So these are our notations. Now, let Fi denote the set of primitive orthogonal idempotent of R of H. Recall that R of H is commutative, so each Fi is a one-dimensional primitive idempotent, and eta I the corresponding normalized class sum of H. We denote Fi hat is phi star of Fi. Now, Fi hat is also idempotent in D of H star because phi star is an algebra map, but it's not necessarily primitive in R of D of H star. So we have we have these sets of chi I characters of D of H, Fi orthogonal characters D of H, and all this of all these elements that we use, and the irreducible characters, primitive idempotent of R of D of H, central primitive idempotence of D of H, and normalized class sum of D of H. But this, as we have a partition, we can now, so this is a set I, the index, these are all the same sets. They are in one-to-one correspondence. But we have a partition of the set I, and this partition is the set of all J, so that F hat J is a primitive idempotent of R of D of H. So this is a set I, and then the partition that we have is, as I said, Fj hat, Fs hat. So this is a map of a primitive idempotent from H star, but it's not necessarily primitive in D of H star. So inside D of H, we take all the indices that are in the same, that Fj hat, Fs hat is Fj hat, that are the primitive inside Fs hat. And this is the partition that we will use later. But this partition is very much the same as like the partition from the connection between this partition and the Nichols-Richmond equivalence relation as another direction. As let's recall that Hopf subalgebras of Kg star, when we have a group of subalgebra of Kg star, are in one-to-one correspondence with normal subgroups of G. And each of subalgebra of Kg star is of the form, it's a quotient, it's the star of a quotient. It's Kg over n for some normal group n in G. Thus, we have this correspondence for groups. But given a normal subgroup n of G, we have, for groups we know it, we have a normal equivalence relations on the irreducible characters of G, where each equivalence class consists of all irreducible characters with the same restriction to n. It's known for group, of course, up to a scalar multiplication. This equivalence relation is expressed in the following Nichols-Richmond equivalence relation on simple subcoalgebras of H star with respect to Hopf subalgebra B. So this is one of the facts mentioned in the beginning, that representation of Hopf algebras resembles representations of groups in the following sense. Let B be a Hopf subalgebra of H star. And we can think about H over N star of groups. We define an equivalence relation on the simple subcoalgebras of H star as follows. Two Hopf subalgebras are equivalent if and only if Bj is contained in BBK, or equivalently, the two characters are equivalent modulo B, if and only if the integral of B multiplied by Kj over Dj is the same as the integral of B multiplied by Kk over Dk. Note that the Nichols-Richmond equivalence relation yields the composition of H star, this decomposition, where Bs is a set of representatives of each equivalence class. Now what we are going to do is to choose a specific Hopf subalgebra, B hat of D of H star. And with this specific Hopf subalgebra, the Nichols-Richmond equivalence relation between the characters of D of H star with respect to this specific Hopf subalgebra that we are going to choose yields the same partition on the set I described above. So from a different direction, we got the same partition on the indices. And what is our preferred Hopf subalgebra is this one. So we take well, I don't know if Mia described these terms, but let's define it. Let n hat is all the elements in D of H, satisfying x1 terms of phi. Phi is the projection, the Hopf projection to H. X1 terms of phi of x2 equals x terms of 1. In fact, this is the Hopf analog of the group theory kernel. That's exactly what it is. And B hat, so this is our preferred Hopf subalgebra, is FQ inverse. I recall FQ is the Greenfeld map from D of H star to D of H. In D of H, it's isomorphism, so we can talk about FQ inverse. FQ inverse of this, it's a left coideal subalgebra. And the B hat is indeed the Hopf subalgebra of D of H star. So this is B hat from one point of view. From another point of view, we have a much better description of this B hat, and this as follows. We have the structure R of D of H, H is quasi-triangular. And if we take R tau inverse, which is another object in H tensor H, then HT is a quasi-triangular as well. And actually, we need to work with T for reasons of op and cop and so on. So to avoid ambiguity, we define FT, phi T, etc. As for FR, phi, etc. And then we prove that this B hat is very clear what of algebra it is inside D of H. B hat is phi star T of H star. So I recall that H star is embedded, when H is quasi-triangular, then H star is embedded in D of H star, via phi T star, and the image of H star inside D of H star, this is our B hat. And this B hat satisfies the following. This is connected with these partitions that we refer to with regard to the indices of the Fi. So we have that for any two characters, chi hat j and chi hat k inside R of dh, this j and k belongs to the same IT, which means that fj and fk are in the same primitive idempotent ft, if and only if these two characters are equivalent modulo our B hat. And now we have a distinguished element inside this partition of these equivalence relations. And recall that CT, the conjugacy class, is also an irreducible representation of D of H. So it has its own character inside D of H. So let chi hat of JCT denote the character of the irreducible D of H model CT. That is that chi hat JCT of an element in D of H, the trace of the representation of the action of P type H on CT. And motivated by Zush and Glynn, we proved the following theorem. Let CT be a conjugacy class of H, and eta T its normalized class sum. Let chi hat of JCT, the distinguished character that we mentioned here, be the character of CT as an irreducible D of H module. Then we have the following maps. We have this character. The Greenfeld map FQ hat sends it to D of H. Phi sends it to H, and then it goes back to eta T. So this is the connection between the character of JCT and the normalized class sum that is related to CT. And the important lemma is the following. So we have this partition. if eta hat j and eta I are the sets of normalized class sum in D of H and H respectively, then phi of eta j hat is eta I, if and only if j is in the set II in this partition. And in particular, JCT is an element of IT star. And with these notations, we have our main result, which I would like to share with you. And this is the main result, and the corollary is what is more useful for us. Let HR be a semi-simple quasi-triangular of algebra. CT a conjugacy class. Chi hat JCT is corresponding irreducible character as a D of H module. BJ hat JCT is a simple subalgebra of D of H star generated by this chi hat. Then we have the composition of D of H star as follows. D of H star is a direct sum over all the conjugacy classes of H, the Hopf algebra generated by them, multiplied by phi star T of H star, which is a certain Hopf subalgebra of H star. Maybe this does not say much or doesn't mean much, but the corollary is the same thing. The corollary is much clearer. And this is the following corollary. Each irreducible D of H module, and now we are talking about a reducible D of H module, is a direct summand of CT tensor VI, where VI is an irreducible H module, and D of H acts on C tensor V. This is an element P of H. It acts on C. It acts on C by bullet, on V by phi T, and which is this formula. But the main idea is that here, in these tensors of each irreducible, each conjugacy class, and irreducible H module, we have all the irreducible representations of D of H. This one need not be irreducible by itself, and we don't know how exactly it is decomposed. We know it for groups, and as I wish to show you, but here we have that all the irreducible D of H modules are summand of this element. And just a small remark that when H is Kg, then R is 1 tensor 1, then this action turns out to be a very simple action. It's just S of P right to C tensor V. So this is the main theorem, and as I said, we don't know much about CT tensor VI for any VI, but we know all we need to know the special case of CS tensor V when V is one-dimensional representations of D of H. So we have a family of representations of D of H representations, which I would like to say a few words about it. How much time do I have?
Oh, let's say another 5 minutes.
Okay. So I will not show you the example with the groups, but I want to show you this special family. So in both we describe a family of reducible D of H models which are obtained from CS by tensoring with one-dimensional H model. So what is this family? First, given an element eta in G of H star, we can modify the action bullet to bullet eta. This modification it appears in Hopf algebras many times. So while the original definition of bullet was H add C and the SP, here we have the eta hits H from the left now. And here we have for eta inverse hit P, a modification. And And actually, we show that CS bullet eta is an irreducible D of H representation as well. So we have now new modifications of the conjugacy classes via eta. Not that any, on the other end, any one-dimensional representation of H is of the form K eta, where eta is a G of H star, so that what is a one-dimensional representation? H hits one, it's eta H1, is some scalar. This scalar is arised from a group-like element eta. So every one-dimensional representation of H is of this form. Based on the above, we obtain a family of irreducible D of H models that are modifications of CS on one hand, and have the form CS tensor K eta, tensor one-dimensional representation on the other. So this is a proposition. Let eta be in G of H star. Then CS tensor this one-dimensional representation of H is isomorphic to CS with a modified action by eta as D of H model. So all the models of the form CS tensor one-dimensional representations are always modifications of conjugacy classes. I would like to mention the important thing that if eta is different from eta prime, then the two representations K eta and K eta prime as one-dimensional are different as one-dimensional H model. However, this is not a one-to-one correspondence. CS tensor K eta and CS tensor K eta prime may be isomorphic as D of H model. So we need to check it, and we have examples in the part that I will not talk about. We compared the representations of D of Kg, which are known, to the representations obtained this way, and we could find when exactly it happens. The two different one-dimensional representations yield when tensoring with CS the same D of H representation. But this is for the next lecture, I believe. So thank you. Thank you so much.
Thank you very much. And I'm sorry about the technical difficulties. Are there any questions? Okay, well, thanks again, both.
Thank you, and I'm sorry I disappeared on you, and thank you, Sarah, for taking over.
Well, originally, I think the organizing committee wanted it to be kind of joint presentation, so
right.
we got it.
If one falls through, the other one is there to help.
A good reason to do research together.
That's right.
So, okay, so I guess we'll take a 7-minute break now till the next talk. Okay. Oh, by the way, my computer also has been giving problems. If something goes wrong, you know, maybe somebody else can take over if you don't hear me saying something. Okay. So let me introduce Claudio Procesi, who's going to talk about tensor fundamental theorems of invariant theory.
Okay, thank you very much. So I will speak about something new, but which has some old origins. So I'll start with something which I suppose everybody knows, so that you have the Cayley-Hamilton theorem, which says that a matrix satisfies its characteristic polynomial, which can be stated as an identity, a trace identity, which involves traces. And then there is a theorem which by now is fairly old, by Razmirtov and myself, which says that all trace identities of matrices can be deduced from this identity, and from the identity that the trace of 1 is equal to D. And so what I want to do is to give a more general This is not going to work. Okay. I want to show that this Kelly-Hamilton identity fits into a sequence of what I call tensor identities, which means that there are identities which hold on tensor powers of matrices. So here are some examples which I hope will illustrate what I am talking about. You have 2x2 matrices, and you have this identity. So here, this is the transposition. This is sort of anti-symmetrizer on two elements composed with this expression. So this is the matrix X tensor the matrix, the identity plus identity tensor X minus the trace X, and this is 0. For this is an example. The other two examples are, this is an anti-symmetrizer on 3 elements, and then you have this other expression. This is now for a triple tensor product of matrices. And here is another one. Again, these identities depend on this, of course, for D by D matrices, you have D plus 2 tensor identities of degrees K, which goes from 0 to D plus 1. And I will explain how this fits into classical invariant theory and how to generalize the theorem of Razmissov and myself to this. Okay. Now this thing does not seem to work well. Okay. So the fundamental theorems of invariant theory, you can read them in the classical book of Hermann Weyl, which are about polynomial invariants for arbitrary number of contravariant or covariant variables for the defining classical group. And he used this to build the representation theory of classical groups inside tensor powers. And so for the purpose, I cannot describe the entirely history of this thing because it's somewhat big, but from my point of view, it's enough to recall Schur-Weyl duality, which is the basic fact of tensor algebra. So you have this vector space V, and you have the two basic commuting operators on V tensor H, the linear group and the symmetric group. The two actions are these ones. And the theorem is that they both span algebras, which one the centralizer of the other. And then together with the first fundamental theorem, which describes some kind of generators for invariants, you have some theorem which is called second fundamental theorem, which describes relations. And in this case, the generators are the elements of the symmetric group, and the relations tell you what is the kernel of the homomorphism from the algebra of the symmetric group to the endomorphism of tensor space. And the statement is that this kernel is non-zero only if the dimension of V is small with respect to H. And then it is the two-sided ideal of the symmetric group generated by the anti-symmetrizer. And so this is the anti-symmetrizer. So this is, of course, the first of a long list of ideas and theorems in representation theory. But then there is another way, which is related to this Kelly-Hamilton identity, and that is to take as representation a certain number of copies of matrices, or if you want, the endomorphism of V in a more intrinsic way, or H tuples of matrices under simultaneous conjugation. And then the theorem is, well, I have troubles with this thing, which doesn't. Let me exit. It's my computer which is not acting properly. Okay. So The multilinear invariants are given through the symmetric group again as these transformations here. And if you have the decomposition of a permutation into cycles, then this formula is the same as the product of these traces of monomials. And for the second fundamental theorem, it is better to extend this to equivariant maps. Equivariant maps from H tuples of matrices to matrices. And then they are just products of traces and products of variables. So they are expressed as elements of what one might call the free algebra with trace. And so let me very quickly remind you this definition, which I hope is more or less known to everybody. So you define an algebra with trace as an associative algebra with a linear map which satisfies the obvious axioms of a trace. And then these axioms tell us that the trace, the values of the trace is a central subalgebra, and the trace is linear with respect to this trace. So this is basically through the approach of universal algebra that this trace is a unary operation in the algebra. So this algebra form a category with maps are trace compatible maps, and they have free algebras. And the free algebra is quite easy to describe. You have the usual free algebra in the variables x, and then you take the polynomials in the traces of the monomials. So what does it mean? Since this is a free object, the trace of a monomial is just the equivalence class of monomials up to cyclic equivalence. So for each monomial, you consider it equivalent to all its cyclically equivalent monomials, and you add these elements as commuting variables, and this actually is free algebra with trace. Then the second fundamental theorem consists in describing in this free algebra what are the identities of a given trace algebra, in particular of d by d matrices. And this, of course, as in the usual theory, polynomial identity gives rise to the idea of a T ideal in this free algebra, which is an idea closed under trace and under substitutions of the variables. And then the theorem is that the T ideal of identities of d by d matrices is generated by the two basic identities, the K-diameter identity and trace 1 equal to d. So this is the classical theory. Let me just quickly remind you how do you define the K-diameter formally. So there is this formula which gives the relationship within the coefficients of the characteristic polynomial and the traces. And then so these are some examples of the formulas you get. And then of course you can define the formal characteristic Hamilton-Cayley polynomial, which in these examples is given by this formula. Okay, so this is the Procesi-Rasmistov theorem that I have already explained. Now this is again there is a long theory afterwards. So if you are interested, I have written 2 papers recently on K-Hamilton algebras, which may be of some interest to people in polynomial identities. Okay, but now I want to go further, and I hope I can go further. My computer is not helping me. It doesn't exit full speed mode. It doesn't do anything. I don't understand what's happening. I'm sorry, the computer is not doing anything. This is quite bad. Your screen sharing, and I'm unable. Let me stop sharing for a second because it's giving me troubles. Okay. Okay, let me share again, and I'll do it without full screen mode because it seems that this doesn't seem to work. Okay. So the Kelly-Hamilton identity can be related to the anti-symmetrizer in a polarized form, in the sense that it is the trace of this anti-symmetrizer times the tensor product of the variables. So this can be understood as a non-commutative interpretation of the anti-symmetrizer. And now I hope, okay, now I hope that things work. And now let's go to the recent work. So that was maybe all known since 40 years ago. So now we generalize the study, instead of equivariant maps from k-tuplets of matrices to matrices, to study equivariant polynomial maps from k-tuplets of matrices to tensor power of matrices. So this is quite more or less straightforward generalization. And these maps form a non-commutative algebra using the fact that tensor power matrices have an algebra structure. And among these maps, for instance, you can find what we call tensor variables. So you take a matrix and then you decorate it with one to some tensor power, that's another. So you place it in some position in the tensor power, and this is certainly a polynomial map which is equivariant. Then out of this you can generate tensor polynomial maps. Then of course you have the traces, and all these ideas I learned as an interesting topic from a guy working on quantum information theory, where these objects are studied for their own reasons, which I don't have time or even the competence to explain. So then what happens? If you have an algebra and you have the usual theory of polynomial identities, and but then you can sort of give an evaluation of the free algebra into A. This extends to an evaluation of the tensor power of the free algebra to the tensor power of A. And therefore, this you can define, for instance, tensor polynomial identities. So the elements in the tensor power of the free algebra which vanish from all evaluations. And this is just one class of objects which one may study. And but then, as I said, I really wanted to take the point of view of equivariant maps. So these tensor polynomial maps are certainly equivariant, but they do not exhaust all the equivariant maps. So you have also the trace tensor polynomial maps in which you also add traces. But then the general tensor equivariant maps contain some extra material. But in any case, these three objects are three algebras, non-commutative algebras, which one might try to study. Now, how do you try to study the third algebra, the equivariant polynomial maps? So take an equivariant map. So this K matrices associates some element on the tensor power of matrices in an equivariant way. So to this one can associate a scalar function which is invariant by adding some kind of extra variables and just taking the trace of this map times this tensor power. So this is sort of a trick which is similar to what one does in the case of connecting equivariant maps to matrices with invariants. So in that case, you just add one matrix variable. In this case, you have to add this n matrix variables. And then, since the trace form is non-degenerate, the knowledge of this invariant, from this you can reconstruct the invariant, the equivariant polynomial map, which actually gives a fairly simple answer. So there are this sort of basic monomial equivariant maps, out of which every other one will be a linear combination. So these are the cases in which you can write it in the following way: the invariant, the previous invariant. So you have this invariant. This depends on the variables x1, xk, and on the variables y1, yn. And we know the form of all invariants. So the form of invariants, I'm sorry, in general is a linear combination of things of this type, where the yi are paired with monomials in the xi. And the final result is that you have the invariant H is the equivariant map H is of the form of this form. You have a product of traces of monomials, so this is an invariant. Then you have a permutation, which is also an element of the tensor power of matrices, because tensor power of matrices are just endomorphisms on tensor power. And out of endomorphism and tensor power, there are also the elements of the symmetric group. So you have invariance, an element of the symmetric group, and the tensor monomial. So this is just a monomial in the variable, another monomial in the variable, and so on. So the first theorem, this is quite easy, that the equivariant tensor polynomial maps are linear combinations of maps given by this formula. Now this, of course, should be formalized. And the way to formalize it is to introduce this twisted group algebra. So here, this is Tx is the free algebra with trace. So then you take the n tensor power over its center, and you take then the extend by the symmetric group, which exchanges the factors. So this is a standard construction in commutative algebra. And then these elements are the formal expressions which evaluated into matrices give the tensor polynomial maps, the equivariant maps. And so the elements of the symmetric group from the point of view of universal algebra are constants, are sort of zero variable elements, which are canonically evaluated by the formula which gives you the action of the symmetric group on the vector space. Now, this algebra is also an algebra with trace if one uses the previous formulas, which now I cannot go back to. And then, so in particular, the trace of a permutation is the trace of its tensor representation. And then the trace of the tensor product is just the formal product of traces. So now you're in a sort of a setting of universal algebra. You have your object, your sort of free object, which can be evaluated in matrices for any size of matrices. And then the question is to understand, when you evaluate this thing in a given size of matrices, what are the elements which vanish? So for n equal 1, this is the classical problem of the free algebra with trace evaluated into matrices. For n bigger than 1, it's a new problem. So that's what I already said, that the second fundamental theorem consists in describing the relations, the elements, the formal expressions which vanish identically when you specialize them in D by D matrices. And there is a classical method which is called Arnold method, which says that essentially one can restrict to multilinear relations. Every other relation is obtained by a multilinear relation by making the variables equal. Okay. So one starts from the basic theorem that the anti-symmetrizer in D+1 element as operator on the D+1 tensor power vanishes, which is exactly equivalent to say that if you have a d-dimensional vector space, the D+1 exterior power is 0. So this is sort of a basic relation. So this gives you a basic relation for D by T matrices, which is this, that since this is 0, since this operator is 0, also when you tensor it by matrices and you take the trace, you get 0, of course. But now you can mix, you take some of the variables, Z are sort of the matrix variables out of which, and some of these are the auxiliary variables. And each one of these now can be interpreted by the previous way of associating to an equivariant map an invariant. This means that the same formula can be interpreted in D+2 different ways, depending on how many of the variables X you choose. So depending on this K, how many of the variables X and how many of the variables Y. Okay. So, and this is essentially the formula that this expression should be identified formally to a tensor expression, so an element of this sort of formal algebra, which I described before, multiplied by this basic object. And if this is 0, this means that this expression here is 0. So this is what the first task that one has to do. So here, what you have, when K equals 0, D or D+1, these things have classical interpretation. So for K equals T, this is the polarized form of the Cayley-Hamilton identity. For K equals D+1 is the polarized expression of the formula which expresses the trace of X D+1 in terms of the traces of Xi. I1 to D, this is just the expression of the Newton function in terms of the smaller Newton functions. And for K equals 0, this is just a relation that says that this is operator is 0 on the tensor power. Okay, but then in general, you get the expressions which I already gave in some examples, in the sense that this, let me go back. This, no, let me go back 2 steps. This thing is a multilinear expression in the variables, but then it is symmetric in these variables, and therefore it's a polarized expression of something, of a one variable object. So that's why you have just one matrix variable, because this multilinear identity is the polarization of this single identity. And here are, I repeat the examples that we had before. So in one case, for 2 by 2 matrices and K equal 1 is this, for 3 by 3 matrices and K equal 1, and respectively for 3 by 3 matrices and K equal 2, you have this identity in the triple tensor power, and this is the second tensor power. So how do you write this in general? Because these are something which you can write sort of by hand, and that's how I started to discover them. Because you see, there is this factorization. There is an anti-symmetrizer times some more or less mysterious expression. So I just have to try to describe you this. So you look at the set of all sequences of integers which add up to I, and then we can define for a given n this tensorial polynomial, if you want, in one variable. That is the sum of x to the h1, tensor x to the h2, tensor x to the hn, over all possible h1, h2, hn, which add up to I. So of course, if n is equal to 1, this is just x to the I. But as soon as n is bigger than 1, this x to the I distributes in all possible ways into the n factors. So these are examples so this is T3 tree. This is a very long, all the ways in which 3 can be added up. So this is 3 is 2 plus 1. This is 3 is 3 plus 0, 0. And this is 3 is 1 plus 1 plus 1. Okay, and then once we have this basic object, then the theorem is that the identity, the tensor identity given by K and D is the product of this anti-symmetrizer times this, which can be thought some kind of tensorial Cayley-Hamilton polynomial, because here are just the coefficients of the usual characteristic polynomial. And here, instead of having the powers of x, you have these powers of x which are spread out over the tensor factors. And so this is the interpretation of those identities. So I repeat, these expressions vanish identically for x a d by d matrix. And as we will see, these are sort of basic identities for these tensor valued objects. They play the same role as the Cayley-Hamilton identity plays for just matrix valued polynomial maps, equivalent polynomial maps. So I hope this is fairly clear. Anyway, this is a explicit formula. You can write it down, you can plug in the matrix X, and you can verify that this is identically 0. Okay. And now there is a generalization of this theorem of Razmissov and myself. And one can prove, and this is not so easy to prove. It requires three pages proof, more or less, that the relations, so the kernel of that map is given, they're all consequences of these deepest two basic relations. But now, of course, I have to explain in what sense they are consequences, because in the usual case, you have the notion of T ideal. And here, what does it replace the notion of T ideal? So we have to define what is a sort of a tensor T ideal. Okay, and so the idea is that instead of fixing a given n, you look at all possible n, all possible formal expressions for all n, which take value in different tensor powers, of course. And each one of these is an algebra. And then you say that the sequence of ideals in this sequence of algebras is a T-tensor ideal. If on one hand it is stable under variable substitution, so you substitute the variables, you take a homomorphism, so the free algebra retraced into itself, and then this induces homomorphism of this algebra to itself. And this idea should be stable under substitution. And then there is the obvious other consequence. There is something vanishes on n tensor, and you multiply a tensor multiplied by another expression, then this should be identically 0. And the same if you multiply it on the other side. Okay, so this means that this ideal tensor, this is sort of formal algebra, plus this formal algebra tensor, this ideal, is contained in the ideal of the tensor, of the sum of the tensor power. And then, of course, once you have this notion of T-tensor ideal, and then the fact that the T-tensor ideal is generated by such as a subset of tensor elements is just that is the minimal T-tensor ideal contained in this thing. And then we can say that these elements are deduced, and it's more or less clear that from these formulas, it should be clear how you deduce a tensor identity from another one. You substitute variables, you tensor it by variables, and so on. Okay. And now there is even a better theorem, which is sort of actually, when I discovered it, it surprised me a little bit. And the idea is this, that this is something which is used quite often in this quantum information theory. That is, usually there is this partial trace. So instead of taking the full trace, when you take the nth power of matrices, you can contract the last matrix by taking the trace. And you have this Equivalent map from the tensor power of matrices to matrices. And so formally, this is this. You have tensor product of n matrices, and this contracts the trace of the last variable and keeps the other variables. So you see this trace, which is actually a linear map from matrices and so on, is really induced by a formal, a symbolic trace. And then this means that you have this symbolic trace from the symbolic algebra of tensors of value maps of degree n to the one in n-1, and this is clearly compatible with evaluation. In particular, if you have an identity for d by d matrices, and you apply this tensor, this t, so you have inside here you have an identity, you apply this t, and you have an identity for lower tensors. Okay, so this looks innocuous, but then one has the following sort of remarkable fact that you recall these expressions, or maybe you don't recall, but recall that I gave a list of these formal expressions which vanish for divided matrices. And so you can apply to these formal expressions this partial trace. And you have to specialize the trace of one already to be D. And then if you do this, it happens that when you apply this formal trace to this formal expression, this vanishes. On the other hand, if you take this formal expression, you multiply by this simple sort of, you add an x as a last variable, and you apply this formal thing, then out of this, you get the next. So you see this as degree k in x. You have added an extra x, so you get something of degree k plus 1. And in fact, you get the next identity multiplied by a simple scalar factor. Okay, so this is somewhat surprising, but not so difficult to prove, except that, and then using this definition, you can define, you can sort of add the operation T in the definition of T star ideal, T tensor ideal. So you can define a T tensor little t ideal if it is a sequence as a T tensor ideal which is closed under this trace, under this abstract trace. And of course, the ideals of identities of D by D matrices is not only a T-tensor ideal, but is also closed under trace. And then finally, the conclusive result is that the ideal of identities of D by D matrices as a T-tensor T ideal is generated just by the anti-symmetrizer and by the identity trace 1 equal to D. So I think this is sort of the best of all possible results because it just puts in evidence, complete evidence, but remark that the Cayley-Hamilton identity is obtained and by a sequence of steps of the previous type. So you start from the anti-symmetrizer, which is for k equals 0, is sigma, this Gothic G, C, I don't know, for k equals 0 is the anti-symmetrizer. And then you keep applying this until you get k plus 1 equals D, which is the Cayley-Hamilton. And this means that the Cayley-Hamilton is obtained sequentially. I'm sorry, where is it? Okay, sorry. Okay, the Cayley-Hamilton is obtained sequentially by this sequence of operations with this formal trace. Okay, I will finish in a second. So there is a simple tool which is used over and over in this theory, which is something which I used also in the proof of the theorem for the Cayley-Hamilton. And this is a very simple lemma that I call splitting the cycles. So if you decompose the set of indices into disjoint sets, every permutation of these M elements can be uniquely decomposed as the product of 3 basic permutations, in which each non-trivial cycle of Taiwan consists exactly of elements of A. Tau 2 is formed by the cycles of tau permuting only the indices in B. And finally, the main property is that the permutation tau 3 permutes only the indices in A. So again, each non-trivial cycle of tau 1 contains exactly one element of A. Tau 3 contains, I'm sorry, why did I do that? Okay, each non-trivial cycle of tau 1 contains exactly one element of A. Tau 3 permutes only the indices in A, and tau 2 is formed by the cycles, permutes only the indices in B, and is formed exactly by the cycles of tau which do this. So this is a simple thing, but using this in a not non-trivial way, by a fairly complicated induction, one can prove that every formal identity which corresponds to an element in the ideal of the symmetric group generated by the anti-symmetrizer and so on, can be deduced from those D+2 identities, and those D+2 identities can all be deduced from the anti-symmetrizer by this construction, which I gave the formal trace. Okay, I think my time is over, and I thank you for your attention, and I hope you like your city, which unfortunately I have not been able to visit this time. Okay.
Thank you very much. Are there any questions?
I enjoyed your talk. And by the way, what about the theory in positive characteristics? What about your theory in positive characteristic?
Positive characteristic, the main problem of course, is that I cannot use polarization. So the formula, these identities, of course, hold in all characteristics because they are defined over the integers. So those basic identities, and also the formula for the partial trace. The point is, of course, that one cannot use directly the Arnold's method. One would have to possibly, maybe, I don't know, I have no idea, but maybe it's possible to use the Zubkov approach to prove also in positive characteristic. This, of course, is an interesting question, but I have not even tried to attack the question.
Okay. Are there any other questions? Okay, so I guess we get back in 8 minutes. By the way, today has reminded me of one of the memories embedded in my memory of two of the great algebraists of that generation, Jacobson and Amitsur, struggling to get orange juice out of a machine at Klein Tower. So I think algebra is, I mean, the tradition has continued, I think.
Louis, when did that happen?
73, when Amitsur was visiting New Haven. I was a student, as a graduate student, and my two idols were there.
I was there in 73. No, I wasn't there at the event though.
No, they were having lunch at the Università. Okay. Oh, we should get started. So our next speaker is Barry Greenfeld. And how do algebras grow?
Yep. Okay. So thank you, Louis, and I'd like to thank the organizing committee for holding this transatlantic conference and for the scientific committee for the invitation to speak here. The title of my talk is How do algebras grow? But maybe a more appropriate title is Why do algebras grow? Or why would we care how do algebras grow? I would like to start with the setting. So we're working over an arbitrary base field, and we are considering infinite dimensional but still finitely generated associative, unital, but not necessarily commutative algebras. So for finite dimensional algebra, the most important invariant is its vector space dimension. The same way that the most important invariant of a finite group is probably its order. What happens if your algebra is infinite dimensional? Well, it's still finitely generated, then we can fix a finite dimensional generating subspace and consider the filtration that covers the algebra. So just powers of the generating subspace. We can assume that the subspace contains 1, and then we really have an increasing filtration that at infinity it covers the algebra, and we can measure, instead of the dimension, which is infinite, we can measure the finite steps, the finite levels of this filtration, and this is the growth function of A with respect to V. Now this function obviously depends on the specification of the generating subspace, but only up to a very natural equivalence relation. So basically, any two such growth functions, I mean, of the same algebra with respect to different generating subspaces, bound each other up to a scale of the argument. And let's see a very easy example. You can take the polynomial ring in one variable and then consider the following generating subspaces: the space spanned by 1 and t, and the space spanned by 1, t, and t squared. Then the growth sequence with the first one is going to be just n plus 1, and the second is going to be 2n plus 1. So these are distinct functions, but they're linear. So this is the way we are going to define the growth rate of an algebra. Just the equivalence class of such a growth function, a modulo this equivalence relation. So it's independent of the choice of V by definition, by construction. And similarly, you can define the growth function of a finitely generated module. And this time, instead of considering just the dimensions of the generating filtration, we consider the dimensions of its action on some generating subspace of the module. And again, it is well defined up to this equivalence relation. Now, what can we say about growth functions? They can be either polynomially bounded or exponential, or anything which is neither polynomially bounded nor exponential, which we call intermediate. So here are some common examples. The tensor algebra always has exponential growth. The symmetrical, well, for V of a dimension greater than 1, the symmetric algebra has polynomial growth, and the degree of the polynomial growth is just the dimension of V. And similarly for the universal enveloping algebra, which we saw in Sue Sierra's lecture yesterday. And in the case of polynomially bounded growth, we can talk about the Gelfand theory of dimension, the GK dimension, which is the optimum degree of a polynomial bounding the growth of the algebra. So this invariant was defined by Gelfand and Kirillov in order to study quotient division rings of distinct Weil algebras. They wanted to show they are non-isomorphic, and for that they used a slight variant of the GK dimension. Now, which values can be assumed by the GK dimension? Then, well, 0 is possible. This is just a case of finite dimensional algebra, with finite dimensional as a vector space. 1 is also possible. That's the linear growth case, as we saw before, just a polynomial ring. And any value, a real value or infinite between 2 and infinity. So, so the 0 case is as I said, is trivial. It's just finite dimensional algebras. The case of linear growth is very special. By the small Stafford-Warfel theorem, these algebras always satisfy polynomial identity. If they're in addition semi-prime, then there are finite modules over their centers. Somehow, the case of GK dimension 2 is under reasonable restrictions. Still, you can say some kind of dichotomy results about it. Anything larger than 2 is in general hopeless to classify. Now, I want to go over some real-life math appearances of growth functions of algebras. So let's start with the classical setting of algebraic geometry. You have finite geometric commutative algebra. You consider its associated affine variety, and the growth function of the algebra is polynomial, and the degree is just the dimension of spec A. In other words, the GK dimension of the ring of global sections is just the dimension of the variety, or the crude dimension of the ring. And also in the projective case, you have a homogeneous coordinate ring, and then you have a deficit of 1. But still, there is this connection between the crude dimension and the GK dimension, the homogeneous crude dimension. This can be carried over to the non-commutative setting of non-commutative projective geometry, which I'm not going to really thoroughly get into, but well, believe me that in the non-commutative setting, you can, for certain sufficiently well-behaved non-commutative graded rings, you can still associate some kind of a non-commutative Proj scheme. And actually, in this case, it turns out that the correct definition of a dimension of non-commutative projective scheme is just through the GK dimension of the underlying ring. So we can think of it as if you take a classical projective variety and you twist somehow its homogeneous coordinate ring. Another scenario of a geometric flavor is that of differential operators. So consider some affine variety, let's say smooth affine variety, even though it has a generalization to not necessarily smooth varieties, and consider the ring of differential operators over it. So we can think of it as just the ring generated by the ring of global sections and the module of derivations over this algebra. then this ring of differential operators has polynomial growth, and the GK dimension is just twice the dimension of X. And as an example to hold in mind, just consider the n-dimensional affine space. Then the ring of differential operators is just the n-Weil algebra, and actually, which has a really GK dimension 2n, as expected. Actually, growth here, the GK dimension here is not just a secondary actor. It plays an important role in, so there's an important notion of holonomicity for D modules. You can think of a module over the Weil algebra, and it turns out that it is very important to analyze and to discuss modules of the least possible GK dimension, which is in this case just m. The next use case I want to introduce is a very specific, but I would say surprising application of growth of non-commutative graded algebras in a completely different area. So fix a global field and consider some transitive subgroup of Sn, and then you were interested. It's very natural to ask how many Galois extensions are there realizing this group as a Galois group. So in general, the answer might be infinite. So it makes more sense to restrict the discriminant. So this is just a number of Galois extensions of K with Galois group G and discriminant bounded by X. And now G and K are fixed, and X tends to infinity, and you're interested in the asymptotics. Male gave the conjecture for the asymptotic behavior of this distribution, of this measure. It's a constant times a polynomial part, the degree here depends only on G, times a polylogarithmic part in X. So this conjecture is widely open, and in particular notice that any non-trivial lower bound for ngk of X would solve the inverse Galois problem. But for small groups, it was proved, it was follows from very deep works. This is in the case of rational numbers, and actually the constants, which I don't really get into the definition of the constants, but the constants also play a very important role in the arithmetic of the field. What I want to show you now is a theorem of a recent result of Ellenberg, Tran, and Westerland, who were able to prove an upper bound of the form of Male's conjecture for the case of positive characteristic. So we consider the ring of the field of rational functions in one variable over FQ, and let's assume that Q is large enough. Then there is an upper bound of the form of Male. So notice that A here, I'm not sure if you can see it, but this degree here of the polynomial part is exactly the same constant depending on G, conjectured by Male. And the polylogarithmic part is a different constant. Okay, so you have to show that the polylogarithmic part actually attains Male's conjectured bound. And Ellenberg, Tran, and Westerland were able to bound the degree of the polylogarithmic part in terms of a GK dimension of a certain non-commutative graded algebra associated with the finite group G. And furthermore, they were able to bound this GK dimension by the order of G minus 2, thereby bounding the polylogarithmic part by the order of G minus 1. So in particular, for Sn, you get almost n factorial. Actually, I said that Q is sufficiently large, but this result is conjectured to hold for all Q. And they were able to show it is indeed the case, provided that a certain X algebra, non-commutative algebra, has sub-exponential growth. So it doesn't have a polynomial growth, but if it has a sub-exponential growth, then they were able to show it is true for any Q, not just large enough Q. And recently we were able to actually accurately compute the GK dimension of these algebras. We computed them as in terms of the group, just the maximum number of conjugacy classes of any subgroup of G minus 1. In particular, we significantly improved the bound on the polylogarithmic part for the symmetric groups, right? Because we improve it from almost n factorial to something exponential in n. Okay, this follows from some combinatorial results on subgroups of Sn. Maybe this is the good news part. The maybe not so good news part is that it also shows that their method can never attain the desired degrees conjectured by Male for the logarithmic part, because the degree here conjectured by Male for Sn is going to be sub-exponential. So anyway, something else will be needed. Okay, I want to zoom out back to some Lie algebras. So you can define the growth of a Lie algebra in a perfect analogy to the case of associative algebras. If you have a finitely generated Lie algebra, if you have a graded Lie algebra with finite dimensional homogeneous components, you can simply consider the asymptotic behavior of the dimensions of the n pieces of this grading. With the finitely generated residually finite, maybe even residually p group, you can associate a Lie algebra, a graded Lie algebra, either with respect to lower central series or p central series or some other reasonable filtrations. And this interplay between a residually finite group and its Lie algebra is very important. It goes back to I guess to a Zelmanov's solution of the restricted Bernstein problem. And in the framework of growth functions, it was utilized by Grigorchuk to show that the gap conjecture for a growth of groups holds for residually p groups. So I'll say maybe a word about it later, but essentially it says that there is no a growth function of a group between polynomial and exponent of square root of n. Lie algebras give rise to universal enveloping algebras. So as we said before, in the finite dimensional case, the enveloping algebra is just going to be of polynomial growth, and the GK dimension is going to be the dimension of L, of the Lie algebra. In the infinite dimensional case, the Lie algebra always has super polynomial growth, at least e to the square root of n, related to the partition function. And it is always strictly more rapid than the growth of L. But somewhat surprisingly, N has sub-exponential growth if and only if its universal enveloping algebra has. So this was observed by Smith, but made even more precise by Petrogradsky, who actually found a sequence of like a hierarchy of growth functions, a sequence of families of growth functions that that translate. So if you start with a Lie algebra of growth similar to one of these functions of these families, then the growth of the enveloping algebra is just going to jump by one step higher. So this gives rise. This is a very nice work. It gives rise to infinitely many dimensions generalizing the GK dimension. So the first family gives rise to the usual vector space dimension. The second is just the GK dimension. The third is a sort of a normalization of the GK super dimension, which I didn't define. And then you have like a continuation of this sequence of dimensions. Yeah, and another relation between the growth of groups and growth of algebras is through the group algebra. So there's a one-to-one correspondence between vertices in the n-bod of the Cayley graph of a given group with respect to a finite symmetric generating subset, and basis elements of the n step of the corresponding filtration of its group algebra. So in this sense, growth functions of groups are exactly growth functions of group algebras. And one last area I want to mention is of symbolic dynamics. So consider a finite alphabet and consider a closed subshift of it, meaning just a closed subset in the Tikhonov topology, which is shift invariant. It is invariant under the shift action. Subshifts give rise to monomial algebras, which are just spanned by all finite factors. And it turns out that there is an extremely accurate and useful dictionary translating dynamical properties into algebraic or combinatorial properties of the corresponding monomial algebras. So a factor complexity of the subshift translates to growth of the monomial algebra. Shifts of finite type correspond to finitely presented monomial algebras. A so-called irreducible subshifts correspond to prime algebras. So the set, the topological nature of the corresponding subshift is going to be just a Cantor set. So we can think of it as the closure of an orbit, which has no isolated points. And minimal subshifts correspond to just infinite algebras. And there is a closely related notion of hereditary languages, which are just, so forget about subshifts, just think of just a collection of finite words over some alphabet, which is a closed undertaking subwords. So any subshift gives rise to a hereditary language, just of all of its finite factors. But in general, there are hereditary languages that do not come from subshifts. And what is important to keep in mind here is that the classes of growth functions of algebras, growth functions of semigroups, growth functions of monomial algebras, growth functions of hereditary languages, all coincide. Okay, so assuming we're kind of convinced that that growth functions are important and play a major role in various areas, it is natural to ask which functions can be realized as growth functions. And actually, I want to start, or maybe up to equivalence, since we have a natural notion of equivalence of growth functions. And I actually want to start with the group case, which is much more rigid. As we saw, the class of growth functions of groups is strictly a subspace of the set of all possible growth functions of algebras. So the polynomial case is dealt with in Gromov theorem, to prove that a polynomially bounded growth function of a group forces the group to be virtually nilpotent. So in particular, polynomially bounded functions of groups are just of the form equivalent to functions of the form n to the d for some positive integer. In particular, there is no fractional GK dimension for groups, right? How about exponential growth? So it's a bit of a tricky question because all exponential functions, if you think of it, are equivalent. So in particular, they're all equivalent to the growth function of a non-abelian free group. But we can ask, we can refine it and ask about realizing specific exponents for real numbers greater than 1 with respect to suitable generating subsets. Okay, so not up to equivalence, but really the exponent of a growth function with respect to some generating subset. So I think the question of whether any real number greater than 1 is realizable is still open. Ershler proved that there's a continuum of possible values, and the recent work of Fujiwara and Sella examines the set of possible exponents for a fixed group. So you consider a hyperbolic group and consider all of the possible exponents with respect to any generating subset or any subset. And then they can say many interesting things about this set of exponents. So, okay, how about intermediate growth functions, which are neither polynomially bounded nor exponential? The first and the most influential example is of Grigorchuk, and it has growth similar to exponent of n to the power of some number between 0 and 1. It says some kind of formula. And there is a gap conjecture. There's a conjecture that there is a gap between polynomially bounded functions and functions of the form exponent of square root of n. And as I said before, Grigorchuk proved it for residually p groups. In general, the only known gap between polynomial and something intermediate is due to Shalom and Tao, who gave a finitary version of Gromov theorem. So as you can see, the upper bound of the gap is very far from the exponent of square root of n. But anyway, that's I think the best known gap result for groups. And Bertoldi and Ershler were able to show that sufficiently rapid, sufficiently regular functions are realizable as growth functions of groups. And in particular, they were able to realize any function of the form exponent of n to the alpha for alpha dense in the interval between the this alpha for the Grigorchuk group and 1. And of course, one can restrict and consider the class of simple groups. So only recently, Nekrashevich gave the first example of a simple group of intermediate growth, constellative monoids as a sort of generalization of groups. So Grigorchuk has a gap conjecture also for constellative monoids. And now back to algebras. So that's a wider class, right? So given a function, when can we hope that it will be realizable as growth function of an algebra, infinite dimensional algebra? There are two obvious necessary conditions. The first is that the function must be increasing, right? Otherwise, the dimensions get stuck at some point and the algebra collapses to something fine dimensional. And the second is some multiplicativity, which is the formula written here. You can think of it in the tensor algebra. Just take an n plus m fold tensor. It is fully determined by its n-fold prefix and m-fold suffix. And let's call these functions natural candidates. Maybe the most interesting question is, most natural question now is whether these necessary conditions are also sufficient. So is any natural candidate equivalent to the growth function of a certain algebra? So let's start with a positive direction, in a step in the positive direction. Smoktanovich and Bartoldi were able to show that any so-called natural candidate is indeed realizable up to a polynomial error term. Okay, so there is a finitely generated algebra whose growth is bounded between your function f and the function times some bounded polynomial factor, and in particular, if the growth function is sufficiently rapid and equivalent to n times itself, so this will be fulfilled by basically any growth function, any function you can think of, which is greater than n to the ln n, then you can accurately realize the function as a growth function. And I want to mention that previously to that, there were known extreme examples constructed by Trofimov and independently Belov, Boris, and Kolatishev of algebras with weird growth functions. So they're oscillating there, infinitely often very close to exponential, and infinitely often n square, or the minimum possible growth. But anyway, the Smoktanovich-Bartoldi result is the first, I would say, a factory result. So it gives you a massive result on realizability, almost realizability of all natural candidates. Okay, and then the next question is whether we can classify growth functions not up to a polynomial error term. And this was, in fact, done by Bell and Zelmanov in a remarkable recent result. They found an additional condition, which is not hard to show. It holds for any growth function of an algebra. It involves the discrete derivative. And conversely, they were able to show that any natural candidate additionally satisfying this new condition is equivalent to the growth function of some finitely generated graded, actually monomial algebra. There's a delicate point here that this condition on the discrete derivative is not an asymptotic invariant. So a function a natural candidate might not satisfy this condition, this discrete derivative condition, but still be equivalent to a function that does satisfy it. So it will be in fact realizable. So maybe the next question is whether this additional condition is indeed satisfied by all natural candidates, maybe sufficiently rapid natural candidates. There's a straightforward corollary of their result, and it's that any increasing sum multiplicative function, called it a natural candidate, is realizable up to a linear error term. So that's some kind of an improvement compared to the Smoktanovich-Bartoldi result. But anyway, the constructions are very different from each other. So let's consider the formal question. It was proposed by Zelmanov, then repeated in a joint paper with Al-Ahmadi, Al-Sulami, and Jain. Suppose you have a function which is increasing and somewhat duplicative, and suppose it is greater than n squared, just to avoid Bergman's gap issues. Is then f equivalent to the growth function of a finitely generated algebra? So recently we were able to show that actually there are arbitrarily rapid holes, so-called holes in the space of growth functions. We're able to show that for any sub-exponential function you take, there is a natural candidate which is even more rapid than this sub-exponential function, but still not equivalent to the growth function of any algebra. So this in particular solves this question, and also moreover shows that it will not hold even if you restrict to sufficiently rapid functions, maybe functions greater than the exponent of square root of n or something. And this should be compared to a very interesting result of Zelmanov characterizing growth functions of modules. So the growth function of a module is again increasing, it's exponentially bounded, but not necessarily sum-multiplicative. And Zelmanov in unpublished work showed that these two conditions, which are very, I would say, obvious, are actually sufficient, necessary and sufficient. So any function, increasing function, which is exponentially bounded, is equivalent to the growth function of a finitely generated module, in fact, a cyclic module over the free algebra. But what we're really interested in is some more restricted classes of algebras. So we're interested in growth functions of objects that either have an additional structure or can be viewed in a wider context of maybe a geometry, dynamics, something with an additional action maybe. And I want to make the following maybe refinement of the realization problem. So we said that monomial algebras correspond to languages, hereditary languages. We say that the language is extendable if any word in it can be extended to an even longer word. In such cases, the languages correspond to subshifts. So you can say that this kind of monomial algebras arise or give rise to a symbolic dynamical subshifts. And again, we have this translation between dynamical properties and algebraic properties, and the algebra has a more, I would say, a natural realization, and it is more a more justified existence. And back to the Bell-Zelmanov construction, if you examine them, you examine the languages, most words are non-extendable. I mean, most words at some point will become non-extendable. So, so that means that there are many words that are non-zero, but you cannot imagine that you have a language that you can say many words, but you're not allowed to say anything about them. So the sentences become very redundant in this language. If you want to think of it from the algebraic point of view, if you mod out by all nilpotent ideas of these algebras, you remain with a polynomial ring in one variable. So the whole rich behavior of the growth function is actually encoded in the so-called junk words. This is not a coincidence. There is a reason behind it. And the natural question is whether we can realize growth functions within the classes of not hereditary languages, but more restricting to extendable languages, or maybe prime algebras. And now I want to make the question precise. So we saw that the space of growth functions is very big and maybe very hard to characterize. But suppose we already know that the function is equivalent to the growth function of an algebra. Then maybe we can realize it as the growth function of some nicely behaved algebra or language, if you prefer this language. Back to the Smokhtonovich-Bartholdy result, So again, I'll just remind you, they proved that any natural candidate is equivalent to the growth function of an algebra up to a polynomial error term. And they left open the question of whether these algebras are prime or maybe can be prime. So even though we observe that they can be some kind of adversarially designed to be non-prime, what is more interesting maybe is that you can always modify the algebras to be prime and moreover primitive. So still monomial algebras, primitive monomial algebras. So primitive algebra is just an algebra acting faithfully on an irreducible module. So primitive algebras are always prime. So that's a primitive monomial algebra. In particular, it is graded and without affecting the growth function. So you can still realize any, in particular, any growth function of an algebra as the growth function of an algebra, of a primitive algebra, up to this polynomial error factor. And in fact, if your function is equivalent to n times itself, as we said, this additional regularity condition, then there exists a finitely generated simple algebra realizing this growth type, which is somehow very much different from the case of simple groups, right? Because this enables to realize many slow intermediate growth functions for algebras, whereas the situation for groups is much harder. And as a corollary, you can also realize growth functions of simple Lie algebras. So this is related to the question of Petrogradsky of which values can be assumed by his sequence of dimensions. Anyway, back to the question of realizability within a nicely behaved family of algebras. This is related and maybe in a way formalized in another conjecture. Zelmanov also appeared in this paper, in this joint paper, and repeated in some slight modifications of whether the growth function of any finitely generated algebra is actually realizable as the growth function of a primitive algebra. So, okay, so suppose you already know that your function is realizable as a growth function of some algebra, just to eliminate, all these weird examples I mentioned before. Can you somehow modify the algebra to be primitive? And as I said before, up to polynomial error term, it's always possible. But however, okay, we're not able to solve this conjecture, to give a counterexample, but we're able to show the following, maybe partial answer for the graded case. So I'll phrase the following theorem in two languages, two parallel languages. One of them is the language of languages, and the other is the language of algebra. So let's start with hereditary languages. So there exists a hereditary language whose growth function is not equivalent to the growth function of any extendable language. Okay, so somehow the inner structure of the language, of the asymptotic growth of the language, forces existence of junk words. And the algebraic counterpart is that there exists a finitely generated monomial algebra that its growth function cannot be equivalent to the growth function of any graded prime algebra, and therefore primitive. So moreover, if this growth function occurs as the growth function of some graded algebra, and we know that any growth function is also the growth function of a graded algebra. This is just a leading monomial argument. It forces existence of non-zero nilpotent ideals. Okay, so this conjecture you at least cannot realize any growth function within the class of graded primitive or even prime or even semi-prime algebras. But the general conjecture remains open. I want to end with several questions. This is a picture of that I borrowed from a creative referee report. So this is a picture of the Oort cloud. It's a cloud of space dust surrounding the sun, and somehow this reminds of the situation in the space of growth functions, right? So you have your space of natural candidates, or maybe the space of growth functions, and for any sufficiently, I mean, any natural candidate, any increasing sum multiplicative function, you can find some kind of a cloud of dust of algebras surrounding it, and even prime algebras and primitive algebras and simple algebras, but still there are many dense holes in this space of natural candidates which cannot be even realized as growth functions of any algebra. I would like to finish with the following questions. So first, maybe a general question. How dense are, in a suitable sense, prime or simple algebras within the space of growth functions? Okay, so it would be also interesting to ask it for simple groups within the space of growth functions of groups. The second question is about growth of Lie algebras. So is there a characterization for growth functions of Lie algebras in the spirit of the Bell-Zelmanov characterization, for example? Now, this time, we do not have to assume submultiplicativity. It doesn't hold for all the algebras. And the only natural necessary conditions we can say is that the function must be increasing and exponentially bounded. Is any increasing exponentially bounded function equivalent to the growth function of the Lie algebra? I don't know the answer. And the last question is some kind of a gap conjecture. So is there a domain, a ring without zero divisors, of intermediate growth slower than exponent of square root of n? So this is some kind of a ring theoretic counterpart of the gap conjecture for groups. I'll just say that I know of two main techniques to construct domains of intermediate growth. One of them is just take your favorite infinite dimensional Lie algebra of intermediate growth and consider its universal developing algebra. But this method will always result in an algebra with growth at least exponent of square root of n. And the other is using group algebras of certain groups, for example, ordered groups. But then again, this reduces to the gap conjecture for groups. So perhaps to answer this ring theoretic gap conjecture, we need novel constructions. Okay, that's all. Thank you very much.
Thank you very much. Are there questions? Okay, so we'll break until for another 9 minutes for Zelmanov's talk. I just want to say that personally, I found these talks fascinating, and I think David mentioned this yesterday. It's such a tribute to Amitsur's memory that what he did has found so much development, even up to the present time. Okay.
Okay, Louis, so we start in 8 minutes.
I think so. Hi.
Hi, Efim.
It would have been interesting to hear your recollections of Amitsur, but I didn't think you wanted to wake up at 4 o'clock in the morning or whatever it is to do that. Oh, well, 5 o'clock in the morning. Well, maybe you want to say something at the beginning of your lecture. I don't know.
Well, I met Amitsur and I tell students that I met Amitsur. When I was an undergraduate student in Novosibirsk, I thought that Amitsur was Japanese.
The name sounds, yeah.
Yes.
You see, I'm also in California. It's a very nice talk. I enjoyed it a lot.
You know, there's this, I forgot to ask Barry, are you still around, Barry? Because
I'm around Zelmanov.
yeah, because
yeah.
No. You know, there's a famous Mother Goose poem. Were you using that for your title? You could say very how contrary.
That was definitely a tribute, yeah, to Avinom's book.
Yeah, you also know that you know, Burrell proved that affine PI algebras have finite Gelfand-Kirov dimension, and Amitsur observed together with Drensky that you could get that from Shirshov's theorem. So in fact, Amitsur did start your subject also, in a sense, or not started, but he was at the start of it. I think I saw Alan Burrell here also.
Hi.
Yeah, hi, Alan. You're in Chicago now, or?
Yep. I'm at my office at DePaul right now.
Right. Very nice.
Do you know how Amitai is doing? I see he didn't come.
You know, he was on the organizing committee originally, and but he didn't show up. So I don't know. I mean, like,
When he has Parkinson's, of course.
Yeah.
Which is a horrible thing to have.
Yeah. He was, yeah, he was, you know, in a sense, Amitsur's, well, I don't know, I guess Aner is straddles group theory and ring theory. But, you know, from the other point of view, you know, Amitai was, you know, great student of Amitsur. So, Fim, are you traveling again?
Not yet.
Not yet.
Not. I read that it became possible to visit Israel, but it's not easy.
Well, if you decide you want to do it, we could make it feasible. We could.
No, they just open, Yefim, they just open the doors in Israel.
Yeah.
Now, I mean, just in these days, I'm not sure exactly what the day, maybe not yet, maybe the 17th of November or something like that. They announced that it will be possible.
But I mean, if you have to stay someplace for a few days or something
No,
like
no,
that?
no, 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 no.
Oh.
You will have to stay at most 24 hours, and it won't. The situation in Israel now, I travel a bit even now. The situation is the following for Israelis, and I think that's going to apply to foreigners. You must take a PCR test when you walk in the terminal. They don't let you get out on the terminal without taking a test. You have to take a test before the airplane, and you have to take another test when you landed. But when you land, it's go very fast, and you get the result. And the rule is that you have to stay in quarantine up to 24 hours or up to the time that you get the answer, the earlier of the two. And in fact, I did it. I went back to Israel just 2 weeks ago, and the answer came within 6 or 7 hours or something like that. So you really have.
We also we went to the States 3 weeks ago, and by the time we got home from the airport, by the time we checked the Kupat Cholim, the health plan, half an hour after we got home, and the test results were already in.
Wow, so it's even much faster. Wow. Okay, so.
But you need the green code. You need a green code.
Yes.
To get into a hotel.
Yes. No, but you can get a taxi, so you're not allowed, I think, there are some rules. You are not supposed to take public transportation, but you are allowed to take a taxi, and you have to stay in the hotel till you will get the results, something like that. Yeah, it's a bit it's a bit, but it's not terrible, actually. It works actually better than in some of the other countries, I must say, because I went to
China, it is 3 weeks.
What?
In China, you have to stay in quarantine for 3 weeks.
Wow, still?
Yes.
Yes.
Wow.
And not at home, in an hotel, and you cannot get out of the room from that.
Did you do that, Ellie?
Yeah. It was 2 weeks. It moved. Now it's 3 weeks, but the third week is not that terrible. You know a thing. If you, by the way, if you go via Guangzhou, it will be strictly 3 weeks. If you go via Shanghai, it will be 2 weeks plus 1 week that will be easier.
I think it's time for Efim's talk, if I see the schedule properly. So should we, can you share your screen?
Oh, don't you see?
It's shared, it's already shared.
Okay, great. So let's get started. And, oh yeah, I see. And so Efim Zelmanov is culminating the 100th anniversary conference with the lecture Brackets and Algebras.
Well, thank you. I feel extremely honored to give a talk at a conference in memory of Amitsur. I was fortunate, lucky to have met Amitsur. Now I tell students that I have met Amitsur. Well, it would be even nicer to be in Israel now, but okay. So let A be an associative commutative algebra. A bracket is just an operation. It's a bilinear binary product. And a bracket is called a Poisson bracket if first it gives rise a structure of a Lie algebra. And second, we have a product rule. Examples. This is the Poisson bracket that you can find in the first chapter of any book on classical mechanics. Another example, let L be a Lie algebra. We consider the polynomial algebra on the vector space L. And so L is a subspace of that polynomial algebra and it generates it. Then the Lie product on this subspace L uniquely extends to a Poisson bracket on the polynomial algebra. The fact that it extends uniquely is trivial because of the product rule, a Poisson bracket is determined by the values on generators. But not every value on generators extends to a Poisson bracket. In this case, it extends. Then a remark that there are very interesting brackets that are not Poisson. For example, this bracket on vector fields on a line is not a Poisson bracket. Therefore, we need to extend the definition. A bracket is called a contact bracket if you fix one variable and make it the identity, then with respect to the other variable, it becomes a derivation. In a Poisson bracket, if one of the variables is identity, it's always 0. But now we demand that it is a derivation. Then it also defines the structure of Lie algebra. And third is a version of the product rule, but more complicated version. For example, this bracket is a contact bracket. And every Poisson bracket is a contact bracket with 0 derivation. So these are classical examples of contact brackets. You see, Poisson brackets are usually defined on polynomials in even number of variables. And contact brackets are defined on polynomials with odd number of variables. So the derivation is, say, partial derivative or this one. And this is a bracket on generators. Again, it's not clear why does it extend to a contact bracket, but it extends. So our goal is the study of Lie algebras determined by Poisson and contact brackets. It is the interesting examples of these Lie algebras are Hamiltonian, contact Lie algebras, and later there will be many more. This program of how properties of Poisson algebras are related to properties of the related Lie algebras is somewhat similar to Herstein's program that he formulated in the 60s. What is the connection between an associative algebra R and the adjoint Lie algebra? He formulated a number of conjectures, and most of these conjectures were proved in 2001 by Baydar, Breschard, Chibatar, and Martindale. We could consider Poisson brackets on a non-commutative algebra as well, but independently, Breschard, Martindale, Myers, and Farkas-Schleitzer proved that if A is a non-commutative prime algebra, then practically all Poisson brackets, if we take the previous definition, are commutators. More recently, there was a series of works by van der Berg, Kantsevich, many others on double Poisson brackets and related double Lie algebras that serve non-commutative situation. It's much more complicated definition. And again, we could consider the connection of double Poisson brackets and double Lie algebras. Probably the same results would hold. We define the center of a Poisson algebra as a set of elements, well, that kills the bracket. And the first step in this program is resolved by Al-Ahmadi and Al-Sulami from a neighbor country, that a simple Poisson algebra gives rise to a simple Lie algebra, which is a direct analog of Herstein theory. Some questions. Let A be a simple Poisson algebra. To which extent the algebra of brackets? Well, we consider the square of the algebra of brackets. Somehow it reflects properties of the algebra A better. So, for example, if we have two simple Poisson algebras, and these Lie algebras are isomorphic, does it imply that the Poisson algebras are isomorphic? This is also an analog of Herstein's problem. Another question, let A be a finitely generated associative commutative algebra. When is the related Lie algebra finitely generated? Or when is it finitely presented? Of course, the second question is much more difficult. Now, let L be a Lie algebra. Let's introduce some notation. We consider the lower central series, that is the series of powers, and we consider the derived series. Let G be a finite dimensional Lie algebra over a field of zero characteristic. We consider the polynomial algebra over it. And then we consider the universal associative enveloping algebra. These algebras are closely related. This Poisson algebra on polynomials is just a graded algebra of the universal enveloping algebra with Poisson brackets that comes from a commutator. So the following theorem shows that the answers, say the question of when the Lie algebra is finitely generated is highly non-trivial. Even in this case, in this very particular case, it is non-trivial. So let G be finite dimensional algebra, as I said. We consider these two Lie algebras, and they are never finitely generated for a non-zero Lie algebra. Now, if we consider members of the lower central series or from derived series, but further members, say power starting with 3, then these Lie algebras are finitely generated if and only if for this finite dimensional algebra there is stabilization of the derived series at this step, at the second step. And that leaves open the question of L squared. For this question, this condition is a necessary condition, but it is not sufficient. We have a counterexample. So this is a delicate question. Now, let's talk a little bit about superalgebras. A superalgebra is just an algebra graded by a cyclic group of order 2. So it is a direct sum of an even space and an odd space. Even times even is even, odd times odd is even times odd is odd. And examples. Let's consider the Grassmann or exterior algebra. These are generators, they anti-commute. And then the basis consists of ordered products. So even the span of even products is the even part of the Grassmann algebra. The span of odd products is odd part. We could, and this becomes a superalgebra. We could consider also G infinity, just the, consider countably many Grassmann variables. For an arbitrary superalgebra, we define its Grassmann envelope. just this subalgebra of the tensor product. And the terminology, superalgebra, it was given in 70s. Superalgebras were introduced in 50s in algebraic topology, but modest mathematicians called them graded algebras, just graded algebras. And then some connections with supersymmetry were noticed in 70s. And so they became known by a much more marketable name, superalgebras, which does not mean that they're superior to other algebras. But, so now let V be a variety of algebras. That is a class of algebras defined by identities. Lie algebras form a variety. Associative algebras a variety, associative commutative algebras a variety, and so on. Now, so let V be a variety of algebras. A superalgebra is called a V superalgebra if its Grassmann envelope lies on the variety. In this way, I have already defined associative superalgebras, commutative superalgebras, Lie superalgebras, and so on. By the way, commutative superalgebras are not commutative algebras. Grassmann algebra is a commutative superalgebra, but it's not commutative. Okay. And Poisson and contact brackets can be superized. There is a rule. If you have an identity and you want to superize it, whenever two variables exchange places, don't forget to multiply by this multiplier. For example, you see here you have BC and here CB. So you multiply by this. And in this way, we can get a definition of a Poisson bracket on a superalgebra. And in a similar way, we can get definition of a contact bracket on a superalgebra. In 70s, at the very beginning of all this area, people even in papers, they explicitly published how a super version would look. Now they no longer do it. They just say super version. Okay, so now we can give more examples of Poisson super brackets, of Poisson brackets on superalgebras, and contact brackets on superalgebras. On the Grassmann algebra, this is a Poisson bracket. There is a simple way to consider partial derivatives with respect to Grassmann variables. And you remember I gave an example of contact brackets. Now we will give an analog. So we consider, this is called, it's almost a polynomial superalgebra. We have one even Laurent variable and n Grassmann variables. And we will define a contact bracket. We should start with a derivation. Again, there are two kinds of derivations. And the first is called, it's physics terminology, Ramon sector. And the second derivation is Negev-Schwarz sector, Y sector. Okay, and then again, we define values on generators. Look, this way. And these values extend to a contact bracket. Why do they extend? It's not obvious, but they extend. Okay, and we denote this Lie superalgebra that arises from this bracket as K. K, 1n, one even variable and odd variables. And they are known in physics as SON superconformal algebras. They were introduced in the paper of 12 authors. The first of them is Adenolo, and also in the paper of Schoutens. And these superalgebras are simple for all n except 4. And for n equal to 4, the square is simple. Okay, Now I will talk about superconformal algebras. There is a celebrated Virasoro algebra. If we take, well, okay, let's the question about terminology. Let's consider all, this is centerless Virasoro algebra. Let's consider all derivations of Laurent polynomials. All of them are of this type. We denote this basis in this way, and then this Lie algebra has a very interesting one-dimensional central extension. And the multiplication is given in this way. This formula was first discovered by Richard Bloch. Then it was rediscovered by Gelfand Dorfman. And then a physicist Virasoro. So this is a counterexample to the principle of Arnold that every concept is named after the second person who discovered it. Okay. And physicists thought that since Virasoro algebra and central extension
applies also to these axioms of Arnold, I believe.
And that Virasoro algebra is so nice, and it's instrumental in so many physical models, that why don't we look for some superalgebra that contains it, which is somehow close to it, and maybe it will be also useful. The first such examples were found by Nevier, Schwarz, and Ramon, and later more examples were found. I already formulated, explained some of them, SON superalgebras. Finally, in '89, Katz and van der Leur published a long survey where they tried to kind of systematic exposition of everything what was known, and they formulated a conjecture that, well, first of all, they formulated a definition of a superconformal algebra. What does it mean, close? So by superconformal, starting with them, by a superconformal algebra, we mean a graded simple Lie superalgebra. Graded simple means that this superalgebra does not contain proper graded ideals. All homogeneous components are finite dimensional, and their dimensions are uniformly bounded, and the Virasoro algebra is contained in the even part. Examples. If we consider this algebras, one even Laurent variable and n Grassmann variables, and consider all super derivations, that's an example. And then there is another series of examples with, say, divergence is equal to 0. It's a parametric family. I won't go into details. Then this family K that I have already introduced. And in that survey, they conjectured that that's it. There are no more superconformal algebra. And this conjecture was based on the recent result on Olivier Mathieu, that in the case of graded algebras, graded simple algebras, where dimensions of all homogeneous components grow no more than polynomially, he classified all such algebras, and they were all of Cartan type or affine Kazhdan algebras. But in 7 years, independently, Chen, Katz, and Grossman, later Shepachkina, found an exceptional, a different superconformal algebra, which Cheng and Katz called CK6. And as for Grossman, later Shepachkina, for many years, nobody knew about their paper, except the authors probably. So this notation just stayed. So now the conjecture is that that's it, with the addition of the exceptional superalgebra, there won't be any more. And there are good reasons to believe this conjecture. I won't give all of them, but I personally believe it. Now, what is known about these superalgebras? Almost all papers in this area were published in Communications and Mathematical Physics. So from now on, it is mathematical physics. Fairley, Newts, and Zakos, physicists, proved that Navier-Schwarz and Ramon superalgebras are finitely presented. Now, and they more or less, they explicitly wrote down presentations. Now, all results below are joined with Consuelo Martinez and Zhezhou Zhang. That's a rare opportunity for me not to be the last author. The theorem. All known superconformal algebras are finitely presented. And if modified Katz-van der Leer conjecture is true, then all. Now, our aim is to introduce superconformal algebras on an arbitrary supervariety. It means that in the previous examples, in the classical examples, there was one Laurent variable. So why one Laurent variable? We will consider an arbitrary finitely generated commutative algebra. But then we have to be careful to give precise definitions. The first is, let A be an arbitrary finitely generated associative commutative algebra. We tensor it with Grassmann algebra and consider all superderivations. This is a clear analog of W. Now, what is K? It's a bit non-trivial. A proposition about tensor products. Let A be a contact superalgebra, so a superalgebra with a contact bracket. And let B be a graded associative commutative superalgebra with a Poisson bracket and with this property. We just modeled Grassmann superalgebra. Then we always can define a contact bracket on this tensor product such that it extends brackets on A and B, and this formula for multiplication of elements from different algebras. Now, in particular, it allows us to construct, well, it allows us to construct contact bracket here and this superalgebra. This is a new class of superalgebras. The side effect are the new examples of simple central finite dimensional contact algebras in prime characteristic. If one day one tries to classify finite dimensional modular Lie superalgebras, that will be relevant. In 98, in a joint paper with Martinez, we have already defined exceptional superalgebras over an arbitrary finitely generated associative commutative algebra. So now we will discuss all these superalgebras and the question of finite presentation. But the question to ask if they are finitely presented is a wrong question. Almost always the answer will be no, except when you have one variable. More correct question is, I need to introduce the concept of a central cover. If L is a perfect Lie algebra or superalgebra, a central cover is an epimorphism such that the kernel lies in the center. And Lie algebra L prime is also perfect. Isaiah Schur proved that among all central covers there is a universal one. He did it for groups, but the proof for Lie algebras, superalgebras is the same. So the correct question is to ask if this universal central cover is finitely presented. And then everything will depend on whether the center of that universal central cover is finite dimensional or not. And that depends on cyclic cohomologies of the algebra A. So theorem, let A be a finitely generated associative commutative superalgebra, and let us assume that we have at least 3 Grassmann variables. Then the universal central covers of all defined Lie superalgebras are finitely presented. I won't discuss now cyclic cohomologies. Now it's a philosophical question. If having odd variables is good or bad. I asked at the beginning, I asked the question, you have a Poisson bracket or a contact bracket. When is the Lie superalgebra or Lie algebra of brackets? When is it finitely generated? When is it finitely presented? And I tried to show that the questions are highly non-trivial. But if we have at least 3 odd variables, then the question becomes suddenly doable. Then, at least on the level of universal central covers, the answer is yes. Thank you. And I want to use the privilege of the last speaker to thank the organizers for their amazing work. One of the organizers lives in San Diego, and I watched during all this time. I followed their work. They worked very hard, and they organized a wonderful conference. Thank you.
Thank you for your kind words, but in fact, the conference consists of the wonderful lectures of the speakers, including you.
Thanks from Claudio to the organizers.
Let us thank the organizers.
Okay, let me thank all the speakers for their wonderful contributions to and to Amitsur's heritage and to us, and we learned a lot. And I also want to extend my thanks to the Israel Institute for Advanced Studies, so for their highly professional work and devotion. So
may I join Aner in thanking all the speakers for really, this was really a great tribute to a great mathematician and who influenced a lot on Israel mathematics, especially algebra in general, and influenced algebra all over the world. I mean, there are many of the people here who were not formally his students, but they certainly consider himself as his moral student in a way, and they worked very hard to make this meeting successful, which I think I hope you will agree that it was very successful. So thank you.
And let me add, let's hope that in the tradition of Passover, the next time we do this, let's do it in Israel.
Oh, yes.
How about in Passover?
Certainly, we certainly hope so.
okay, so see you all soon here on site.
Not in San Francisco, or where? In New York? Where are you? Where is your background? The Gazzano Bridge?
Yeah, this is the Golden Gate Bridge, yes.
Golden Gate. But you're not there.
No, no, I'm not there. I'm in Jerusalem.
I thought this is Jerusalem.
Yeah, well.
Yeah, we could put also background that we are on the moon or something like that.
That's the Jerusalem beach in Tel Aviv, right? And so.
Yes, you're right. It's close to Jaffa. It's in the
So you
south.
could call this the Jerusalem Bridge.
Okay. So probably we'll get many more tourists.
I take a photo.
It was a wonderful conference. I personally thoroughly enjoyed it. Thank all the lecturers and organizers.
Thank you.
Thank you.
Okay, we'll see you sometimes.
In Jerusalem.
That's right. We'll work on it.
When we're freed of this COVID.
Okay, bye.
Bye-bye.
Bye-bye all.
Bye. Ciao, ciao.
Bye, thank you all.
Bye.
Thank you.
Leave.